It's always a linear combination of these elementary product operators, okay? So any operator here is built from a linear combination, sum of elements operator on this space only, tensor operator on that space only. And then you just say, all right, the partial trace, I know how it's defined on this thing alone. And then you say, I want it to be a linear operation. So the partial trace of C is defined as you take such a decomposition. And that's it. Then you have defined it on any operator. Does it make sense?
Yes.
Okay. In fact, we will use this today later on. So it's good that you asked. What else? Okay. So let's continue with this open model here, open system. Okay, so again, that's a lot of text here, I realize that. But it's just sort of recall. Okay, anyway, so again, the wave function of system plus path, of atom plus path in the interaction picture is this phi. And the evolution equation of this, the Schrödinger equation of this in the interaction picture, we derived what this was this thing with interaction Hamiltonian, which consisted of a single operator. It was the interaction operator, but it became time dependent because of the free dynamics. Anyway, and there were these three directions, well, in which sort of phi can be expanded, and these vectors are written here again. And my task now is, for example, to figure out what is this number C1. And this is a very standard procedure that you do. How do you get from this equation the C1 out? Well, this is a vector equation if you wish, right? Because all of these guys are vectors. So what people would do, you take the projection, you take the bra acting on this whole thing, on the left and on the right. Okay? And what you get for on the left, you have the time derivative on the left, right? So phi dot, this c dot, this goes away because this is time independent. So phi dot is c dot 1 and d dot times the chi's. If I apply this on here, on the left-hand side, I get just C1 dot, because this, when it takes the inner product with psi1 is 1, and this is orthogonal to all of these, so this gives 0. Does it make sense to you? So taking the projection onto psi1 of the left-hand side is just this function here. Does that make sense? It's a very standard procedure. And on the right-hand side, I have to take the bra of each of the terms. This gives 0 because C1 is orthogonal to psi1 is orthogonal to psi0. This gives 1 times C1, and so on. Okay. But actually, sorry, I didn't do that. Actually, I took the projection also of this thing here, and I know what this operator is, and I use this expansion for psi here. All right, so this is what I wrote here. And I know what this operator is. It's written again here. It had two terms. It was this freely evolved sigma plus b and sigma minus b star. And if you calculate this, I will not do the details, but it's very, very simple because you know everything explicitly here. What you get is this term here. Okay? What I'm saying is that this sum here is simply taking the projection of this right-hand side on C1. How do I do it? I know explicitly this. I know explicitly that in the sense that this has this expansion here. And I use the orthogonality between psi1, psi0, and chi k. Okay. So this gives me an equation where the derivative of C1 is expressed in terms of the functions dk, right? The dk's are also unknowns, of course. There are these components here. But at least I have a relation among these two. And now I can do the same, of course. I can project this equation onto any of these directions. I just did a projection onto psi1. Now I'm doing a projection onto a fixed k, psi k. And if I do that in this equation, I get a relation between the derivative of the d, here it is, and the c. And using the explicit form of all the operators involved, this is what you get. Okay. Ooh, somebody told me I shouldn't use yellow color yesterday, and they didn't change my colors. I'm sorry about that. Okay. Anyway, in the post-it notes, you will see everything. The projector will not distort colors. Okay, so I have a coupled equation. C1 is coupled to all of the dk's, and the dk's, each dk is coupled to the C1. All right, and now I'm saying, let's look at the situation where in a formula, all the dk's at time 0 are 0. Okay, again, what are the dk's? The dk's were the amplitudes. Decay at time 0 is the amplitude of the initial state in on the vector where the kth oscillator is excited. I'm saying let's put these all equal to 0. So let's have the initial excitation only on the atom. So if I choose this initial condition because it's convenient for doing the subsequent calculations, I assume that initially the cavity has no excitation, and I placed in the cavity an excited atom. Well, if that's the case, then I can just integrate this equation, right? Or at least, I can take the integral. If I take the integral, the time derivative here becomes the function itself, and then this is the integral here. Just integrate that, and the initial condition, if you have put stick in t equals 0, I get the integral from 0 to 0, that's 0. So that's good for this. Otherwise, I would have to add here the initial value. Anyway, so I get now an expression of d, not d dot, because I just integrated this expression of d in terms of an integral over c. Okay, very good. And then I can stick this here expression I got for d in terms of c. I can stick this back into the equation which expressed c dot in terms of d. And if I do that, right, if instead of this d, I put this integral in here, I get an equation, integral differential equation for c. The derivative of c is the integral of some function, which involves this and everything, times c. This is this c here, okay? So I have eliminated the functions d of k. This is now only a function an equation involving c alone. Of course, it's still not easy because c is on the left side with a derivative and on the right side with an integral. So we still don't know what c is, but we will be able to say something about the properties of c. Okay. So c dot is given by the integral of c. It's also called a convolution if you wish. It's convolution of c with this function f. And what's this function f? If you look at these explicit terms here, it turns out to be this thing here. Okay? And you realize, and again, it looks like a bit arbitrary for this special situation here, but that's a very general thing happening. This f here is actually what's called the correlation function of the reservoir. So sure, in this example, we got this out here explicitly as a result for this f. But if you look at other models, the structure is similar, and you figure out that whatever stands here is usually this vacuum correlation function. What's this vacuum correlation function? It's the average in the vacuum state of the reservoir alone. The vacuum state is where each oscillator is in the ground state. So it's the expectation in this state of a certain product of two operators, namely the operator B, which and B star, which were part of the interaction. And one of those has to be taken at freely propagated time t, the other at the freely propagated time 0. That's called vacuum because this state here is the vacuum. And correlation function, well, because this is at time 0 and this is at time tau. That's what people call correlation function. Okay, so how can we say more about this? And now comes a philosophically and mathematically and probably physically important sort of aspect. You know, what happens if you couple, like we did now here, this atom to 1 oscillator, 2 oscillator, 10 oscillators? In terms of when you look at times, how this stuff evolves, the thing is that if you have finitely many oscillators, finitely many degrees of freedom, then the dynamics always turns in circles. It means the dynamics is always quasi-periodic, right? I mean, you can easily feel how this goes because you see, if you have, this is sort of what, this is the propagator, this is what determines the dynamics, right? So any state psi of t, I'm taking kind of a step back here. It's not this specific for this model, but in quantum theory, right? If this is initial state, you have your Hamiltonian, this is the state at time t. But what if, as I said, if you have finitely many degrees of freedom, whatever that means, if this H, this is a self-adjoint operator, let's say a matrix, what if this H has the form, you know, you can diagonalize it, so it has eigenvalues Ej, and then eigenprojections, well, maybe let me put them like this. Right, whenever you have a matrix, you can always diagonalize it like that. These are the eigenvalues and eigenprojections. Well, I think you might know that if I know that H is like this, then I can also write e to the ith. In mathematics, this is called the functional calculus. You can find any function of H by just taking the function on the eigenvalues. It's a good fact that this is correct. And so if I apply, so you get a sum here, and so all of these e to the ite, these are oscillating factors, right? Because the e being an eigenvalue for Hermitian matrix is real, so this is just oscillating. And so if I apply this now to the initial state psi naught, what do I get for psi of t? Psi of t is the sum, right, e to the it ej. Okay, then I have the overlap of psi j with the initial state. Let me call this Cj times the direction of psi j. Kept. Okay. All right. So these are a bunch of vectors for each j1, and each of the vectors I multiply with such a phase here, and they add up the result. And as a function of time, what does this do? Well, each of these guys rotates around a circle, right? Does it make sense? Each of these things is actually periodic in time because you just rotate around the circle. So if t becomes large, then you just move. This is a complex number. It moves around the circle. And so here you have a bunch of terms. Each one is sort of periodic, and you add them up. So the whole thing will be sort of crazily oscillating, but forever, right? I mean, you know, if t is very large, whatever, this keeps oscillating. But is this what you expect in nature? No, because you know that stuff is irreversible. right? For example, in what we're trying to do in this example here is we have this initially excited atom in the cavity. We're trying to model spontaneous emission of this atom. So the atom should decay to the ground state, and then the photon or whatever the excitation should be given to the cavity, and that's it. The atom doesn't go back up. So stuff is not always periodic or quasi-periodic, right? In fact, in open systems, that's sort of a trademark of open systems. Stuff is irreversible, right? And so the question is, well, if on the one hand, we have this property, but on the other hand, physically or philosophically or whatever, you expect irreversible dynamics, how is this compatible? And the answer is, well, I guess the answer can be manifold. The answer can have to do with scales of times you look at, or maybe equivalently, sizes of systems you look at, or maybe equivalently, in more mathematical terms, how close together these eigenvalues are, or in a limiting situation, if sort of you think that I have many degrees of freedom in this H, so the sum is humongous, and actually these E's, they're very closely spaced, then you could think, well, kind of in a limiting situation, this sum could be an integral. And oops, what happens if you do an integral instead of a sum over J, you integrate in sort of a limiting situation, as I said, then you have here the Fourier transform of a function psi, the Fourier transform in the variable t. And I don't know, but it's quite easy to see that the Fourier transform of any decent function, if it's a little bit regular, will actually decay in time t, okay? So you do get this decay in time t, which means this irreversible dynamics, if instead of looking at finitely many constituents of your system, and in this situation, it will be the number of oscillators, if you replace that by infinitely many of them, so that the spectrum becomes very intricate, it's called continuous spectrum, then formally these sums turn into integrals, and in these integrals, from very simple mathematics, you know that this decays in time, and you do get irreversible dynamics. Does this make sense philosophically? So,
there's a question online.
Yes.
They raise their hand, so possibly I can allow you to talk a minute.
Sure. Okay. So this procedure, this formal procedure, I guess, is called the continuous mode limit. And actually, that's a struggle that I personally have, because I'm in my research, I try to do stuff mathematically correctly. And of course, theoretical physicists do their stuff correctly in their discipline. But there is this sort of, not fight, but there's slight tension that, so if you look at how people do this, and incidentally, this is how I present this, they do some calculations. They start off with a finite number of oscillators. They get some formulas, just like we did. They get some formulas. That's what we did. We got some formulas. This formula, for example. How did we get this formula? Well, we assumed, because you can see that there's a sum here, that we have finitely many, or maybe countably infinitely many, but it doesn't matter. So let's say finitely many oscillators, so you can do calculations. You don't have to ask yourself too much what you're doing in terms of convergence or whatever. And then you come to a stage where you want to read some physics into this, and then you're stuck because you used finite dimensions. Maybe numerically you're not stuck, but at least analytically, you can't keep going with this. You will not ever see decay in this. even though you think decay in time tau, even though you think physically this should have decay. So then the theoretical physicist says, okay, fine. I started off with a sort of different model, but now I do an infinite volume limit, which is what I do here because it's easier. And then they get some sort of irreversible physics out. But you started off with a model, and then in the middle of something, you change the model, and then you get what you want, is the procedure. And it's a very standard procedure. And I'm not saying it's wrong. Well, I don't know if it's right or wrong, but to me, it's not satisfying. So what I do in my research is I actually start off with a model where, to begin with, you are saying, well, I do start off with a true reservoir, which has infinitely many degrees of freedom, and then I don't have to do in the middle of my arguments this kind of limiting thing. It gets very intricate because oftentimes, you know, there is this limit of having to take in continuous modes, but oftentimes people are interested in what happens time asymptotically, so you have a limit of large times often. And often models are complicated, so you have some other called maybe coupling constants, whatever, that you want to take small, otherwise you cannot say anything. So there's another limit of weak coupling involved. So there's tons of limits because otherwise you can't say anything. And so, as you know, sometimes, unfortunately, interchanging the order of limits is not always giving the same result. So, for example, if I first take the volume to infinity or this continuous mode limit and then take time to infinity, I get a different result than when I do the opposite order of the limits. And so there's all kinds of questions appearing, which in the literature, because I think they are a bit difficult sometimes, they're not always addressed. Anyway, so that was a little bit of philosophy. But there is other views too, I guess. They would say that, why do you spend your life trying to do this in a correct mathematical way? We know anyway it works. And if you just do, I guess, computer simulations, which I don't know how to do, then none of these questions are relevant because time cannot be infinity. And in a computer, you cannot have infinitely many modes anyway. Okay, and so it's a question of time scales and stuff like that. Not easy, but interesting. Okay, so let's do the continuous mode limit now. We have this sum here, and we will turn it into an integral by saying that we make the environment more and more complex, more and more oscillators. So instead of summing over the label of the modes, mode 1, oscillator 1, 2, 3, and so on, I could rather sum over all the frequencies of the modes, okay? So because if I have a bunch of oscillators, they're indexed by k, I can collect all their frequencies, omega 1, omega 2, omega 3, some of them might be the same, and so I can just sum over all the frequencies instead. And then I have to, well, to get the original sum, I have to split this sum into a second part here over all the labels of the modes for a fixed frequency, okay? So this is total equality sign. It's just a different, it's a change of variables if you wish. All right, and then you could also, okay, I remind you maybe what this GK was. This GK, sorry, I have to scroll up a little bit because it has a meaning, physical meaning. It's in the Hamiltonian, it's telling you, so about that here. Didn't talk much about the GK so far, but this GK is a complex number, and it sort of tells you how strongly the mode K is willing to engage in an exchange of excitation with the reservoir, sorry, with the atom. If this GK for a specific oscillator K is 0, it means that oscillator does not couple to the atom, and it doesn't exchange any energy. If this GK is huge, then the mode K will be strongly coupled to the atom. Okay, so this is a bunch of numbers, complex numbers in general, which govern how strongly each of the oscillators interacts with the atom. Okay, so these numbers now, they show up in this sum. And then I could say, well, instead of viewing G as a function of K, of the label, I could say I will view G as a function of the actual energy of the oscillators. Okay? So then this sum here becomes just the total number of oscillators having a given frequency omega times the modulus squared of this function G at this given omega. Okay? It's just rewriting this sum into a form that you can see will become an integral. Okay? So far I have, without this blue stuff here, I have my quantity that I want to. This quantity here is given by that sum here. And now I really make this look like an integral. I say now I assume that my distribution of energies in my reservoir, in my oscillators, is spaced by delta omega. So I put more and more and more frequencies in this oscillator field, and the frequencies become very narrowly packed, and delta omega is sort of a typical distance between these frequencies, and we'll make this equal tending to 0, and then this is just the Riemann sum of an integral, okay? And so what you see is that this quantity, I'm scrolling up again, this thing here. Why was this important? Because this was essential in getting this coherent, this equation for this function C. That was this f here, had this form. We're analyzing this f right now, and this f happens to be now given by, in this continuous mode limit, by this integral. Okay? And this is the, okay, I should have said something else. When I did the trick here of multiplying and dividing by delta omega, I have this ratio. This was the number of oscillators having energy omega, and here I divide by delta omega. So in the limit, this gives the density of all oscillators having energy omega. And maybe somewhat unluckily, I wrote rho for this density, because rho is not a density matrix, it's just a probability density, so to speak. Okay? Anyway, so this function, this correlation function up there is actually turns out to be of this form. Okay? And as I mentioned there, sort of, this function is actually a Fourier transform, because you see here the Fourier factor of a different function, which is this thing here. And the function, it is a Fourier transform of this here, modulo 2 pi or something, for definitions of Fourier transform, whatever. This is called the spectral density of the reservoir. Okay, so the correlation function is the Fourier transform of the spectral density. And as I mentioned there as well again, it is a general, very, very general fact that Fourier transforms, they decay. They decay in time, or here in tau. This is very easily visible. This decays very quickly if the function you take the Fourier transform of is quite smooth. So if you have well-defined derivatives of a function, then its Fourier transform will decay very quickly. Okay? This is also sometimes known as the Riemann-Lebesgue lemma. Very easy fact to prove and very general. Okay? So the message here is continuous mode limit leads to decay of the correlation function. Okay? All right. And now we're still doing this. We're still doing this, trying to figure out properties of this of this function C1 of t. And so the question now is, well, what should we take for any of these quantities, which will fix all the other quantities? Like, what should we take for, what's the reasonable form of the spectral density? You see, that's a quantity of the reservoir that tells you about the reservoir, about the interaction, but also about, as we said, the number of oscillators per energy. And what's reasonable for such a function? And if you are a good physicist, like Professor Garraway, This is from one of his papers in 97. Then you look at microscopic models and you figure out what is a reasonable form for a spectral density. And in this paper, it was shown that one of these reasonable form would be this. This is a function of omega. Omega is non-negative. And this is what's called the Lorentzian. It has 3 parameters. There's an overall coupling G, I guess. Then there is this non-negative number capital gamma. And there is a omega c at which this Lorentzian is peaked. Okay, if you draw a picture of such a function, it looks like, well, what I drew there. It has a peak at a given omega c. The peak is given by essentially the ratio over G over gamma, because you see gamma over gamma squared is 1 over gamma, so G over gamma. And the width of this Lorentzian here, like if you go halfway up to the maximum, the width is actually this gamma. So if this parameter gamma is large, then the spectral density is very flat in the sense that you have oscillators of many, many, many different kinds of frequencies. If this gamma is very narrow, is very small, then almost all oscillators must have frequency close to this omega c. And I guess what actually the gamma and the omega c is depend on the geometry of a true cavity in a lab, right? Okay, now a very nice thing is that we shall take this form of the spectral density, and then you can actually calculate, I think pretty much explicitly, these quantities for that specific form of the spectral density. Okay, and what you get for C1 in the end, so let me just go back to what the C1 was. This was the C1, no clue what it is. I take for F, which is the Fourier transform of the spectral density, I take a specific spectral density, this Lorentzian. Then I can calculate what F is, and I can figure out what C becomes. And C actually now finally has a solution, okay? And this is an explicit solution. It has been derived in this paper, which I refer to here, by Li, Zhao, and Shao. And they found this form here. It's a bit of a calculation. Okay, so this is a specific form of C1, which we can now analyze. What does it involve? It involves a parameter, delta, which is the difference of omega naught minus omega c. Who are these omegas again? This omega naught is the frequency of the atom. So the transition energy, the level, the distance between the two levels, energy levels of the atom. And omega c is where the spectral density of the noise is concentrated. Okay. The difference between these two is called detuning parameter, this delta. And if this delta is 0, then you say that the model is at resonance. Okay. So the transition frequency of the atom is exactly where the spectral density is highest. Okay, that's the one parameter that's involved here. Then there's another parameter, this, oh, we still got the gamma, of course. That is from the spectral density of noise, so sort of the half width. And then according to this paper by Li, Zhao, and Zhao, there is another number R here, which they calculate to be, well, given by that number. And that number is given by a square root of something. And that something involves the geometry of the cavity by this gamma and the G and the detuning delta. Okay, this number here is a complex number in general. And so, oh my God, you have to take the square root of a complex number. That's totally doable. And you should take the principal branch. Anyway, I'm just saying that this is a very explicit formula with now a few parameters coming from the geometry of the cavity, as well as the detuning. By the way, here, okay, so that's, of course, time is essentially present in all these terms here. And this is the hyperbolic cosine and the hyperbolic sine. You see that generally this C is a complex number because, you know, this here is complex, there's complex here. Since R is complex, the cosh will be complex, the sinh is complex, everybody's complex. Okay? All right. Okay. We're almost done with this model, don't despair. What did we do? We had initially a cavity in the vacuum state, and the atom density matrix was given by this. Then we took the Lorentzian spectral density, and we found this explicit value of C1. Here it is explicit, but still, we're now interested in seeing what happens as time becomes, let's say, large. Okay? And it's still not so easy because even though it's totally explicit, right? I mean, this all is complex, and this has a complex phase here, and so on. But you can look at special cases. If you look at the resonant case, where this detuning is 0, then the formula for C simply reduces to that here. And the R, okay, again, an exponential factor. There was a delta in here sitting before, but that's 0 now. So an exponentially decaying in time factor, multiplying some cotangent and hyperbolic cotangent and sinh. These, of course, are also exponential in time. So, you know, you have to be a bit careful. Anyway, and these are not because the delta is 0. In the above formula, it was just R. Now it's called R naught. Happens to be the root of this quantity. Let's look at the situation where what's in the root here is non-negative. So if the cavity is so that the spread of the modes in terms of frequency is relatively wide, so gamma is bigger than this parameter 4g, then this is a non-negative number here. I take the square root, R naught becomes just a non-negative number. I can stick this back in here and see what happens for time, as time goes on. In fact, then you also see that this here becomes just real, okay, if R is positive, because then all of these functions are real. So there's no imaginary part. And you can see from that formula that C1 has this simple shape now. Okay, it's the initial condition and then times the exponential. I mean, actually, that was the formula we had before. Sorry, but the gamma here now becomes explicit because we know the C's and so on, okay? And the gamma, so this form we knew from before, and this gamma is now explicitly given by this quantity here. Still not totally easy if we want to know, for example, what happens as gamma if gamma is large or small. But now you can discuss and you can see. If I take times which are relatively small, so that R naught T over 2, which is what stands in these cinches and coshes here, is relatively small, less than 1, you do a Taylor expansion, and you find out that this gamma of T, remember, this will have to be integrated here, this gamma of T as a function of T in this regime, and with all these assumptions, is actually proportional to T. Oops, proportional to T, okay? So for small times, you have here something which is proportional to T, well, tau here, the integration variable. So this will be proportional to tau squared, T squared. If I integrate T, I get T squared, okay? So at small times, the decrease of this function is governed by Gaussian behavior in time, okay? And what about large times? Well, if instead of RT small, you have RT large, you again expand and see what happens to this ratio. And if you do that, you see that gamma of T then becomes roughly constant, okay? So if gamma of T is constant, independent of time, then in the form of the decoherence C1, this is independent of time, so this integral will be proportional to time. So for large times, this C of T will decay exponentially quickly in time. For small times, it decays like e to the minus t squared. And that is our discussion. So here's the summary. The reduced dynamics shows irreversibility, the reduced dynamics of the system alone, of the atom, which means time decay, because we coupled the atom to a continuum of oscillators. And this C of t, which essentially governs, the C of t actually is the off-diagonal density matrix element of the reduced system density, atom density matrix is proportional to C of t. We just saw that when t is large, C of t goes to 0 exponentially quickly for large times. So the final state is when this is 0, this is 0, and you have probability 1 here and probability to be on the excited state here. What this shows is that you do get the transition from initially excited atom to finally de-excited atom, because the final state here is the de-excited ground state. Okay, and even more, you know how quickly this process happens, kind of. You know that for large times, once again, this happens exponentially quickly in time, and the onset is like e to the minus t squared. Okay, that's what we figured out, and we figured out one other important piece of information. We figured out that, and that's why this exercise is so important for you. We figured out that that was the content of the exercise, that the equation of motion of the density matrix has this specific form. Okay. It had this S of t and gamma of t. S of t is hidden in this effective Hamiltonian. Anyway, this was the imaginary part of the C, which was 0 in some cases, right? Anyway, so, and this gamma of t, which is this decaying factor here, gamma of t, it's the guy, this guy here, which we sort of managed to handle at least in some time asymptotic regimes. Okay, and we figured out that this gamma of t for large times becomes constant in time. Okay, so if we look at the evolution equation of the atom alone for large times only, there's a little simplification. This gamma actually becomes the final value of the function gamma of t, which becomes constant as we just saw. Okay, and so then this evolution equation, let's also look at the resonant case, in which situation this H effective is just the original HS. The evolution equation has this simple form. Derivative of the reduced density matrix is given by a commutator term plus this gamma, which now is a constant, times another term, an operator acting on the density matrix, which is this whole shebang here. This is incidentally was showing up on one of Camille's notes yesterday. Okay, and so the evolution equation more succinctly can be written as derivative of rho is some operator, linear operator applied to rho, and this linear operator has two parts. One part is the commutation with an HS, another part is called the dissipative part. It has the structure that was above. And so, well, if you have an equation, derivative of rho is L applied to rho, this is very simple to integrate, at least formally. Rho of t is e to the TL applied to rho naught, right? Because if I take the derivative of this, the L comes down and I get my equation here. That is great because the structure of this equation is totally simple. After all this work, you know that indeed the evolution can be expressed very simply. If I know what this L is, let's say I know it very well, and so I would be able to know this thing very well, then it would be very easy for me. You give me an initial state, rho naught. I want to know at time t what it is. I just apply this known operator here to your initial state and I get the answer. So we bypass all of this complicated stuff that we did. once we have arrived at this easy structure. And remember, maybe you do, at the beginning I told you the dynamics given by the Schrödinger equation has a simple structure. It's this e to the ith. Okay, or for density matrix, you have to take e to the ith on one side, e to the minus ith on the other side. But the point is there's a structure. There is a central object, the h, the generator of the dynamics. And if you know that guy, you know everything. And I told you, if you take the reduction of such a simple, you know, Hamiltonian Schrödinger evolution, you take the reduction of that evolution to a subsystem, then it's complicated. And it's not of the form of e to the ith effective or something for a subsystem. Okay? But what we did here is just saying that actually it is in this situation. Because there's again a structure, right? All I need to know is this operator L, and I have the structure that the dynamics is given by e to the TL. That is special and crucial here in the sense that we took this equation for gamma of t constant. It's one thing, right? We looked at the long time. What is the structure of the evolution equation for long times? And it turns out, oh, it's actually rather simple. It does have a structure. In fact, it's a group, right? Because, you know, e to the t plus SL is e to the TL, e to the SL, even for operators. So this has a group structure, just like the Schrödinger dynamics has. But this came from some approximations, right? Approximations of large time, and even for large times, right? This gamma is only roughly that. So if I wanted to look precisely at the true evolution, it would not be of this form. This is an approximation. And so there are two questions. One question is, well, let me first say the second point here. One obvious question is, if I have the true evolution of a reduced system, it is not going to be of this nice, not going to have this nice structure. But, like in this situation here, am I maybe able to find a regime of parameters somehow, as we did here, so that the true dynamics is well approximated by such a semigroup or group e to the TL? Can I justify, can I control, can I find the difference between a suitable e to the TL dynamics, which would be an approximation to the true dynamics? That's a very important question in this field. And if you can do that, then you say there is a Markovian approximation to your dynamics. The Markovian approximation is this guy. It's called Markovian because it has this semigroup structure. Okay? This is a hard question. This is a hard question. I mean, well, it is a hard question, I guess, numerically and from a theoretical physics point of view and from a mathematical point of view. This is a hard question. Another question is very interesting as well. Let's say you are able to find a Markovian approximation. Okay, so let's say for some reasons, just as we did in this model, we were able to find some L. We found an L, an explicit L, right? This L here it is. This is the L. It's explicit for this model. Let's say you know what the L is. Let's say you know that you can find a Markovian approximation. Again, this is difficult, but let's say you know that. And then you can look at the dynamics generated by this Markovian approximation. This is the dynamics. You take an initial state and you apply this propagator to it. That's an approximation to the true dynamics. But you can ask yourself, what must the properties of this generator L be for this to be actually a density matrix, right? Because this is supposed to be a density matrix. So the question is, what is the general form of what people call a super operator L? Because this operator already acts on operators because it acts on density matrices. So what's the generator? What's the general form of an operator L acting on density matrices such that for all times, this thing here is again a density matrix. And this question, number one, can be totally solved and is the starting point of a rich, opportunity of studies. Because as we will see together, today and tomorrow, there is a canonical form of such an L, which has a few ingredients. But once you know that any L making a Markovian dynamics has a specific form, then you can just go into this form and choose the constituents of that form and make a ton of models that give all kinds of Markovian evolutions for you. So you have a toolbox. By this L will generally have a few parameters. By changing these parameters around, you get a whole world of possible models of Markovian dynamics. And you can see what kind of effects you can get. And you don't have to go back and think, oh my God, there is a reservoir, and how do I derive this and that? No, you can say, whenever I have a Markovian approximation, I can play with what this L is and see what I get out by just analyzing this. Okay? That's why this is useful for the practitioner. Do you have questions? Where's the mic?
Yes, sir. I just want to understand what motivates us to choose the spectral density, because I see we are using the Lorentzian. Can we use the Gaussian? And also, what other spectral density can we use?
I have no idea. SSS, no, I mean, but excellent question. But I told you I got this from Professor Garraway's paper. Do you remember? Maybe you can give instead of a talk. Well, actually, take your time.
So the original work was perhaps in a slightly different direction. Now I'm thinking I might include a few slides on this aspect in my own, which is not going to be about this topic originally. But the original motivation was to try and understand better the pre-existing, and we're talking 1997, the existing derivations of where you're going with super operator L. In many ways, the derivations that we had around at that time were a bit, hairy in places, let's say. So we're talking about time-dependent second-order perturbation theory with a lot of terms and a lot of tricks to simplify things. One wondered how correct it really was. And so this work in 1997 was finding a pathway through where you could, within certain approximations, do things exactly. Okay, so that was the idea. Now, to answer the question about the Lorentzian, basically the origin of the Lorentzian was from optical cavity physics. So people can map out cavity resonance by letting a little bit of light in and looking at the resonance that you get, how much light is staying in at a particular frequency and how much is reflected, like you would with a Fabry-Perot resonance, for example. And you can also do the theory of the resonance of cavities. And then the Lorentzian is a reasonable approximation to the real resonance. It's not actually going to be the same as, if you do Maxwell's equations and solve what would the modes of the cavity be like, you will get some corrections, and those can be interesting. But the purpose really of using Lorentzian, which is a standard approximation, was that within certain weak coupling limits and so on, it leads to the simplified solution of exponential decay. Yeah. And that's a nice sort of safe home base to be operating at, to do more complicated things. So it's from several angles. Reasonable physical approximation, not going to be exact for all modes, but it's reasonable. And secondly, leads to a very simple result of exponential decay.
Thanks a lot. More questions? Can you pass the mic?
Thank you. Does this model give Rabi oscillations as well in some limit when you have a very narrow spectral density or something?
Dr. Garraway.
So not really as stated here, because the Hamiltonian part here is sigma plus sigma minus, and that's just an energy part. There's no driving term that will give you Rabi rotations at present. I don't know. Perhaps Marco will be adding that later. I don't know the plan exactly. But if you would add in something into the Hamiltonian part, and you can, then you can potentially have a driving Rabi rotation going on in the system.
Thank you. I wasn't planning, and I don't have knowledge, to further make this model more complicated and so on. But my plan was to address question number 1 here. What is the general form of a superoperator so that this here generates, for each time t, a density matrix? And that is the part 2 of my lectures. It's about CPTP maps. And that's more linear algebra-y with a physical interpretation of things. But what comes now is more technically, is more like study in linear algebra. Okay? And I will take 10 more minutes or so to start the topic and then continue tomorrow. Okay. The word CPTP will show up a few times. I think some people call it only CPT, but what it means is completely positive trace preserving. C for completely, P positive, T trace preserving. Okay. And here is the physical motivation, but in a sort of abstract way, I guess. We're dealing with bipartite systems. So we have 2 Hilbert spaces, a Hilbert space H and a Hilbert space HR. This is supposed to be the reservoir or bath Hilbert space. And we have a pure state of the reservoir given by a vector, normalized vector omega. Okay. And we also have something playing the role kind of a dynamics, or maybe a one-step dynamics. People call it a quantum channel. Anyway, just a unitary on the full system, full complex system plus reservoir. Okay, so these are the actors. And now we define a map, phi. How do we define this map phi? First of all, what's the input of the map phi? The input is, well, physically it's going to be a density matrix. Okay, but let's just view that phi can be, you can feed phi any bounded, any matrix on HS. In particular, you can feed it a density matrix. That will be the physical interpretation at the end. So phi acts, it takes as an input an operator on the Hilbert space of the system. And well, the output is again an operator on the Hilbert space of the system. And it has a certain structure. What do? First, you take the initial density matrix or operator X of the system and you tensor it with the pure state of the reservoir. So this means that if X is the density matrix of the system, you have here not entangled, a product form, a product state of system and reservoir. And the reservoir is in this given fixed state omega, which we fixed to begin with. Okay, and then on this initial density matrix, you act with your dynamics or one-time dynamics or something, some action by this unitary, general unitary U, right? So you can think of U as being e to the ITH. Then you would have here e to the ITH on the left of the density matrix, combined density matrix, and e to the minus ITH on the right hand. And so that would be just at fixed time t, the dynamics of the state of the whole system. All right, and finally, you take the partial trace of this full density matrix at time t, if you wish, or after you applied U. You take the partial trace, you trace out the reservoir, and you are back with an operator on the system, on the system H alone, right? Because if you remember, the partial trace, the input of the partial trace is an operator on the whole tensor product space, but the output is only an operator on the system times some complex numbers and add it up. Okay, so the partial trace maps huge matrices on the tensor product into just matrices on the system alone. Okay, and so that's why the image of this map phi is again just operators on the system alone. Okay, and in fact, the question that somebody had this morning, and I put on there, is also again treated here. If you have an operator which is of product form like this, then the trace, and this is the R reservoir, the R section, the R factor, okay, and you take the reservoir, the trace over R, then the trace of this thing is just keep this alone and take only the trace of C. This gives a number, and again, this is the definition of the trace, and then you extend by linearity. Okay, so I want to find out in a first calculation today, let's take another 5 minutes. I want to carry out this partial trace here using this recipe. Okay, well, to carry this out, whenever you have to calculate a partial trace, you need to write, if somebody gives you a C and you need to take the partial trace, you can only do that by finding what the decomposition of C is in terms of these A and B's, because that's how the partial trace is defined. It can only apply the partial trace by definition or use the definition of the partial trace on things like that and linearity. So if I want to do this partial trace, and again, this is general, if you want to do partial trace of anything, you need to find a decomposition of this in a sum of operator on the left space times operator on the right space. Okay, so I don't know what this U is. This is a general operator on the whole tensor product Hilbert space, but I know it can always be written just like I wrote here as a sum of operators on the left and the right space. Okay, I put also here coefficients, which I didn't put there. It doesn't matter. Okay, so this is the definition of phi. In preparation of having to take the trace, partial trace here, I will write now U in this form and U star in this form as well, with the star, of course. So this seems to be giving a complicated term here, right? So Ij is the summation of this U here, gives one double sum Ij. Then from U star, I get another double sum KL. And the coefficients have, because I have the adjoint, the coefficients have to be taken complex conjugate. But the good thing is then I have to take the trace. I can pull all the complex number outside of the trace, right? That's why they're here. But then I have to take the trace of this thing here. The good thing is that this thing here is of product form, so I can apply the definition of the partial trace. So I have a Pi times Qj from this U here. And I have a pk times ql, different indices from the double sum coming from this U star here, where I use again this formula. Okay. So this here, I don't know if this is crazy to you or easy to you, but if you do this for a few times, then it's not hard. So this thing here is just, I can collect Pi on the left side, on the left factor, Pi x on x and then acts P star K. That's everybody on the left factor. And then on the right factor, Qj, omega, omega, and then this guy, Q star L. Okay, and so you see that this shebang is actually of product form, something on the system times something on the reservoir. And now I can apply the definition of partial trace, and I have to take the partial, I have to leave this alone. That's what I wrote here. And I have to take the trace over the B part, over the reservoir part, which I wrote here. Okay. And then I have to remind myself, what does it mean to take the trace? And taking the trace can be done in the following way. You write your operator in any given basis, and then you sum up the diagonal elements. Okay, so take a basis, call it F alpha of your Hilbert space HR, and then the diagonal elements are, well, I take my operator and I cat and bra this operator with the same basis element. So for fixed alpha, this is the element, the alpha element on the diagonal of this operator, okay? And I have to sum over all of them to get the trace. Does this make sense? No, yes? May I ask you directly, does this make sense? Thanks that you answered. I was pointing at him, but yes. Okay, sort of. Sort of is good. It's absolutely totally trivial, would also be good. But I think we're in between. What I'm saying is that here's an operator. It acts on a Hilbert space with basis E alpha F. That's a basis. I'm saying, what is the trace of an operator A? Well, I have to look at the diagonals and add them all up. Sum, right? How do I get these diagonal elements? Each of these is a number. Well, the alphath one, this guy here, the alphath density matrix, the alphath element on the diagonal is given, of course, by, this is written in this basis, F alpha, A, F alpha. Yes? I mean, that's what the nature of a matrix is. The matrix elements are obtained by taking the inner product of the matrix in the given basis in which this is represented. So if I want to add up all the diagonal density matrix, the diagonal elements of A, I simply have to add up all of these for each alpha. It is an interesting, nice fact that it doesn't matter which basis you use. Of course, the individual density, the individual diagonal elements will vary as you vary the basis, but their sum is always the same. The trace is invariant under, base changes. Okay, so that's what I'm doing here. This was the operator, what I called over there A. I take the alpha diagonal element and the sum over all alpha. This gives the trace. And so I'm replacing this here by the sum over alpha. Okay, and so what I get then is, all right, I get a sum over alpha from here. I get a sum over ijkl. That's from there. But the thing is that, see in the sum over alpha, because this is a rank 1 cat bra thing, if I take this overlap here, I get one number times another number. And it sort of it separates the J from the L, in the sense that this is now a sum over the alpha of products of numbers. One depends on J and one depends on L. And so I can distribute what depends on J in this sum, and what depends on L, I can distribute over this sum. That's what I did. I pull the sum over the alpha out, and then I distribute, as I said. And okay, my voice is starting to go. On the left side, I have pi, but these are just numbers. So I can put this on the left side too, and some ij goes on the left, and then analogously on the right. Anyway, it's a simple, well, way of rewriting things. But now we see that there's actually a structure. It looks in principle a bit complicated, but there is a structure. The structure is that the map phi is actually obtained as follows. Stick x in the middle, and then multiply with some operator on the left, some operator on the right, and then sum these operators up. These operators on the left and the right, they're not the same, but one is the adjoint of the other. You see, if I take the adjoint of this operator, the star goes away. This becomes the complex conjugate. You use properties of inner products to see that this is this in complex conjugate, and the complex conjugate of this is just this here. So the form of this map is, if I define this whole shebang to be equal to one big operator, call it K alpha, because it only depends on alpha, right? Because I sum over ij here. So the ij is just a dummy summation variable here. Once I've summed, it doesn't depend on ij, it just depends on alpha. So this phi has this very nice form. It's of the form, stick x in the middle, take a bunch of operators K alpha, put them to the left, put the star to the right, add up. Okay. And these operators are called Krauss operators. And it's amazing, okay? It's amazing. Maybe this derivation is not totally amazing, but it's amazing what follows as a consequence of a map having this structure, okay? So we just saw that the phi, which was obtained by sort of physical consideration in a sense, right? The way I obtained this was really from the reduction of a combined bipartite system with an action U, a dynamics or something else, a quantum channel, and the reduction to a small system. It has this Krauss structure. We will also figure out what some of the properties of these Krauss operators are later on. But as we will see later on, well, tomorrow, it's the only option, every map which has certain properties, okay, is of this form. So there's a sort of universality in these maps. This was not very clear, but it will become clear next time. And so I will stop here, but answer any questions if you have any right now.
I can slightly modify my answer that I gave before, just to be correct, because I realized there's another way of looking at the previous question. So before this section on Krauss operators, and that is to take this spectral density, the Lorentzian, and make it very narrow. And then you can get something which is called the vacuum Rabi oscillation if the atom is excited as the initial condition. It will tend to try and exchange energy with this very narrow mode, assuming it's resonant. If it's off resonant, you're in trouble. And this is a single excitation rocking back. It's not the usual kind of Rabi rotation where you apply an external field, which is what I was thinking of in the previous answer. But you can get this so-called vacuum Rabi oscillation, which was something that was of interest years ago because it's an exchange of energy between the excited atom and the vacuum.
Mhm. Yep.
Yeah, so it's,
Thanks, guys.
Hier, ek dink is op die Summer School website, sal
Okay.
daar wees. Daar's 'n sign up en dan kan jy dit direk kry. Dit is automated. Gaan doen maar net gou daar as jy nie reg om jy dit weet maar net vir my. Vra vir Graham waar jy dit kan kry. Graham sal vir jou presies kan. One. There you go.
Thank you.
Perfect.
Okay, I think we can start. So yeah, let me just hand straight over to Camille.
All right, so let's start again and continue where we left, where we stopped yesterday. So yeah, I make a brief recap also. So yeah, what we saw essentially is so yeah, what's the notion of heat and work for quantum systems, and so yeah, these slides recap a little bit that. So yeah, any exchange of energy between the system and either the environment and the driving system, or in other words, any change of energy of your system of interest can be split into contribution, one called heat and one called work. And these two contributions, so the first one is, you can do a zoom. So this one, which is associated to change in the state of the system. And the second one, which is associated to work and is related to change in the Hamiltonian of the system. Okay, and we saw that these two definitions are largely inspired by the definition in stochastic, in classical stochastic thermodynamics, and also using this definition, we recover that this quantity here is actually related to energy change promoted by the external action. So similarly as classical thermodynamics, while the other term associated to or identified to heat is at the end of the day results from the action of the bath. So again, similarly as in classical thermodynamics. But you also commented that this, let's say, simple and nice definition starts to be questionable in two situations, which is actually most of the time the situation which starts to be interesting in quantum physics, which is when the bath is finite. And that gives the example of, so here we have, our system of interest interacting with the infinite bath. And now we have the extreme opposite situation. We have a very finite bath, even a single harmonic oscillator. And I say that we can be happy to identify the change of energy of the bath as heat, but in this situation, we tend to do the opposite, to say, okay, the energy change of the harmonic oscillator, very small bath, it's more associated to work. Okay, and there was, so I made this comment that I can come back on in a minute. that yeah, actually, if you take a laser in a coherent state, large coherent state, it can be approximated as generating a time dependence in the Hamiltonian. And the second situation is when we have strong coupling. Yeah, the main question is, so what's when we have strong couplings, the interaction of energies, it cannot be neglected. And so what we do with this quantity? Is it I mean, should we associate that to the energy of the system, the energy of the bath? Is it work? Is it heat? Yeah. And so yeah, we saw two possible extension. So this one, which is quite simple and widely used, which is to say, okay, all the energy of the bath is associated to heat, which end up to say that the energy interaction is included in the splitting of heat and work. The second extension, which meant to be if you want a refinement of this one, is to say, okay, in some situation, as I just mentioned, for instance, when the bath start to be very finite, we don't want to say that the whole energy change of the bath is associated to heat. And so, yeah, in order to do that, we defined, a notion of thermal energy and non-thermal energy, and this variation of thermal energy is associated to heat. The variation of non-thermal energy is associated to work. Okay, but I didn't give much more details about that. There was a good question about when we drive externally the system, and yeah, I said if one of the system is driven, it's fine. If both, it's kind of limitation also of this framework. Okay, so now I'm going to present a third extension, possible extension. So to take into account strong coupling, but just before that, I promised I would come back on this question of the laser. So I added some notes. So which are the following. So yeah, we consider here our qubit interacting with our harmonic oscillator. So the associated Hamiltonian is this one. I mean, could be this one. It could also think of other kind of Hamiltonian. So where this is the energy of the qubit, yes, sigma z, Pauli matrix, and here we have a coupling between sigma x and this, which correspond to the position operator of the harmonic oscillator, and this is the canonical free Hamiltonian of the harmonic oscillator. So if you are not very familiar to that, we can actually make a general, in a similar way, general statement. You have just two system A and B, two quantum system A and B, which are interacting. So you have the free Hamiltonian of the system A, free Hamiltonian of the system B. Whoops. And yeah, they are interacting with two observable XA and XB, which can be any observable. And so the dynamics of this, of the joint system AB is given by the Schrödinger equation, or here, if you use the density operator as a von Neumann equation, Liouville von Neumann equation. And again here, so we are interested ultimately in the state of A. So we are tracing out B, the partial trace of a B. And so what you obtain when you expand that, so here we substitute in the total Hamiltonian, we substitute this decomposition here. It's not working. Yeah, this one. Okay, and so you obtain 3 terms. So the first term is this one. It's like correspond to the free evolution of the system A. The second term is this one. It includes so the interaction between A and B. And the third term is this one. It's related to the free evolution of the system B. And since we are tracing out B, you can show that this term is actually always equal to 0. Okay, so we end up having only 2 terms. The first, again, is a free evolution, and the second term is, yeah, the interaction. And again, this is precisely the difficult term, and which gives rise to all the difficulty of open quantum system and so on. But if you do a very strong approximation, which start to be valid if, for instance, you system B, in the case of the laser, is in a very large state, you neglect, so you can neglect the, or another way to see that is also, yeah, you neglect the correlation and you see what you obtain. And if you're not satisfied with what you obtain, say, okay, maybe my approximation was a bit too strong. I can take the, so yeah, you start to do a perturbation expansion theory. You can start to take the first order correction to that and so on. So yeah, neglecting the correlation, it means that you will, for each state, A and B, you will take the local state. Okay, so you are tracing to have the local state or the reduced state of A, you trace the joint state AB over B, and for B, you trace the joint state AB over A, okay, and you obtain that. Now, if you substitute, so this expression into the top one, you obtain that. Yeah, it's too small. Yeah, you obtain that. Here I open the, expand the commutator, so there's 2 terms. XA, XB times the discorrelated state and the other way around. Okay, you compute the partial trace with respect to B. You obtain XA rho AB times the partial trace of B. And here's the other way around with the other way around in the partial trace. Okay, now the point is that, as I commented, the trace is invariant over circular permutation. So it means you can take rho B there, or you can take XB there. Again, if you do that, you see that these 2 expressions are the same. So you can put that in factor. So what you obtain at the end is x of t, which I define it at, so this trace of the operator xb with respect to the state of B, and so the commutator operator xa time state, the local state of A. All right, and so now if you, so yes, this is what we obtain for this state here. So if we substitute in the dynamics, what you obtain is simply of this form. So here you see that, yeah, what you see imaging is this contribution here, which correspond to a time-dependent Hamiltonian. Okay, so you see that if you neglect the correlation between A and B, the resulting dynamics is a unitary dynamics with a time-dependent Hamiltonian induced by the local dynamics of B. Okay, and so if we apply that for the laser, so the laser is described. So the coupling will be typically a coupling with the electric field of the laser. So which is written like that. So it's identified or associated as if it was the position operator of an harmonic oscillator. The dynamic of the laser, we will approximate it as only the free dynamics. Okay, and if we assume that the laser is initially in a coherent state, so of this form, you can compute that. And if I didn't make any mistake, you should obtain something like that. Okay, so you see you have directly an explicit expression which depends on the amplitude of the coherent state of your initial coherent state, which is again the state of the laser. And so this approximation of neglecting the correlation between A and B, again, this is not always a good approximation, but to describe the action of intense laser on the two-level atoms, this is a very good approximation, at least for short times. Okay, so that's how you can mathematically show that if you have a large quantum system which allows you to neglect correlation, it ends up behaving as a driven term in your Hamiltonian. Okay, and this description is also often called semi-classical description, which means that we describe the laser as a classical system. Okay, so now let's go back to where we stopped. So this is I'm going to make it zoom. So this is another framework suggestion to try to answer these two questions: what we do when the coupling is strong, what we do when the path is finite. And so this quite recent paper suggests the following. So you take an arbitrary system, your system of interest S, coupled to a path. Okay, so here you have your Hamiltonian here. So actually here, there's a small, I think I just did a copy paste. What they consider is that there is no external drive, okay, at least for at this level. So they just consider time independent Hamiltonian for S, time independent coupling, and time independent Hamiltonian for B. Okay, so I will correct that. Maybe I can even do something like that. So there is no time dependence. Which would be actually also a limitation of this framework. I imagine they are planning maybe to extend that to the situation where there is drive, but for now it's an undriven system. Okay, and so we assume as yeah, very often that the system and the bath are initially uncoupled. And we trace out the bath. Okay, and we obtain what's called a CPTP map, and that Marco just explained us. And going a bit further, if the inverse of this map exists, yeah, this you can ask Marco. If the inverse of the map exists, you can define the dynamic, or better to say, the dynamics of your system can be expressed like that, where L is called the generator, and it's so it will be defined in this way here. And yeah, and this is what's called master equation. And now you can show that the requirement of emissivity and trace preserving impose a structure of this form. So yeah, Marco will probably do something like that. And yeah, so this is a similar form as we just saw for a two-level system, but it's generalized to arbitrary systems. So instead of having only two possible jump between the ground state and the excited state, you can have several kind of jump, which correspond to this summation here. Okay. But yeah, the details are not very important here. But so we have two kind of contribution, as always. One contribution, which is so this one, and you recognize as a unitary contribution, and one here which maybe you don't recognize, but it's a non-unitary contribution. It's a dissipative contribution, and it's describes the action of the bath on the system. Okay, and so what's important here is that Ks, this operator appearing here, I already mentioned that, but in general, this Ks will be different from the, and here again, there is no time dependence, is different from the local Hamiltonian of your system. Okay, and so the point is that this operator Ks of t, which in general will depend on time, is associated with the physical dynamics of the system, and therefore it's a proper operator to compute the energy. And so they will define, or at least the original plan is to define, okay, we take this operator, which has this physical meaning of describing the dynamics of the system, and we use the same convention as we did before in the weak coupling limit, meaning that if you take this term, you take the time derivative, you will obtain two terms, one associated to the time derivative of the state, the other associated to the time derivative of this operator. And then we say, oh, okay, so we know that, we say, okay, so this corresponds to the heat. And this is another typo. And this corresponds to the work. So here it's not W, it's K of S, right? I will also correct that before sending the notes. One more wrong copy paste. Okay, but there's an issue, which is the following, is that actually the master equation doesn't have a unique form. And you can show that for also this operator L, which has a jump operator or sometimes called Lindblad operator, they are not unique. So you can change, or you can define, you can to each jump operator, you can define a new jump operator in this way, where alpha k is a complex function, okay, and multiply here by the identity. And if together with this change in your jump operator, you do the following change in your operator k, so you take the initial operator k and you add all this term here, and beta is another arbitrary function, then it's guaranteed that the total dynamics remains the same. In other words, as I just said, this form, of the master equation is not unique. You can decide to describe that with another set of jump operator and with another operator Ks. And then it starts to be problematic, because if you decide that Ks is the energy of your system, and on top of that, you will define what is heat, what is work, but then you realize that actually I can choose almost, I mean, not almost, but I have a large degrees of freedom on how I choose these Kas. At the end of the day, what you're defining as the energy, heat, and work, it's doesn't have a strong meaning. Or in other words, it means that you could choose different Ks, and you choose which would result in different heat flow, in different workflow. And so which one is a good one? So their solution to that is to define a notion of minimal dissipator. So they defined an inner product between super operator. So geometrically, you can think of something like that. So this is, imagine that quality of the image is not that great. Imagine you have, so this is all this three-dimensional space is a space of a super operator. So the generator of your master equation, the generator of your dynamics, and this vector here corresponds to the actual generator. And so what I said is actually, so this is fixed by the initial choice of initial state of your bath. The coupling of the bath, this is fixed. But what is not fixed is how you decompose that into this unitary part and dissipative part. Okay, which geometrically you can, so with this inner product, you can define a hyperplane which would correspond to the unitary part, which is this green one, and all the orthogonal direction correspond to the dissipative part. And so you see that this vector, you can decompose this vector in many ways. So you can, for instance, take a component on this unitary part like that, and you will have the component on the non-unitary part like that. Okay, so you see you have an infinite way of decomposing this blue vector. But so what they are saying is, so using the structure I mean, defined by this inner product here, which I won't go into detail. They say, okay, we're actually going to take the following decomposition, the one which minimize the norm of this vector here, which means they choose the dissipator of minimal norm and the norm according to this inner product here. Okay, which geometrically correspond to that. You decompose this your operator in so one component on the unitary part and the orthogonal component to minimize the norm of this of this dissipative part. Okay, and doing so, you define a unique. You have a unique way of defining your dissipative operator, and therefore a unique way to define the unitary part. And yeah, at the end of the day, a unique way of defining this operator Ks. One observation which is not useful here, but it's I think important observation is that when you see the expression of this norm, you say, okay, I get my master equation. Now I have to deal with this norm to minimize the dissipator with this norm. So in practice, I will not able to find this minimum. And what they show, or maybe it's another paper will show that, but someone showed, I don't know how, but actually, if you have a dissipator which is composed of jump operator which are traceless, meaning if you compute the trace of the jump operator and it's equal to 0 for all jump operator entering into your dissipator, this is actually, it means that you have actually this dissipator of minimal norm. Yes?
What is the psi and the phi in the product? I mean, on the left side, it's just L1, L2, right?
Yeah, so this is it's arbitrary state, and you take the average over all states, psi and phi.
Oh, the bars is an average.
Yeah. So it's very complicated. Yeah. Anyway, so yeah, the point is that with this convention, they have a way to define this in a unique way, this operator Ks. And so with that, we use we apply again this usual definition that we saw initially. So Ks will define the energy of the system, and when you take the time derivative, the term associated with the change of the state of the system is associated to heat. And here the same typos, the other term associated to the time derivative of the operator Ks is associated to work. Okay, so this is another possible framework. And lastly, I will mention very briefly, I won't enter into detail because it's also get technical quite quickly. And this one is based actually on what is done classically for classical thermodynamics in strong coupling with bath. So here again, the hypothesis is that A and B are initially correlated. And one of the hypotheses is that B is an infinite bath. Okay, so again, we start with this, joint Hamiltonian. And so this framework is, there are many papers. I gave some of the main reference on that, is to use what's called the mean force Gibbs state. So the mean force Gibbs state, so it's defined like that. So physically, what's the meaning of that? What's the intuition? Is that here I have my system S, okay, interacting with B, and the assumption, intuition, is that at a long time, if S is small compared to B, B is very large. If also you have this is the right kind of coupling, like if you have a dephasing coupling, this won't happen. But forgetting about some details. You will assume, you will imagine that the global system SB actually tend to a thermal state. Okay, so this is which is the maybe I don't remember if we already mentioned that explicitly. Maybe I should clarify that. So for arbitrary let's put like that, for arbitrary system S with an arbitrary Hamiltonian S and given let's say temperature Ts, we define the thermal state of S, associated to this Hamiltonian at this given temperature as minus Hs divided by KBTS. Okay. And here you divide by the trace of that. Okay, and this quantity here is called as a partition function, but you can see it just as a normalization term, because you see now if you take the trace of that, you will have the trace of that divided by the trace of that, it's 1. So you have a normalized state. And KB is a Boltzmann constant, and this is often rewritten like that. With here I can see G, because it's this function here, and we defined very often we like to be a bit lazy in physics, so we define beta S as the inverse of KBTS. Okay, it's a bit messy. So sorry. So what's inside the partial trace, you can now recognize this is the okay. Sorry, this is thermal state associated, so thermal state of the joint system SB at the inverse temperature beta, which is the inverse temperature. I didn't put it here, but this is the initial inverse temperature of the bath. Okay, and so the idea again, if you have a very small system, an infinite bath, this is not this small system which is going to change the temperature of the bath. Okay, and so if the final state if you at long time of SB is indeed this global thermal state, it means that the local state of S is obtained just by tracing out B. Okay, and this is this mean force Gibbs states. Okay, and so if you can neglect the coupling between S and S and B, by doing this partial trace, you will just recover the thermal state of S. Okay, which means that your system thermalized at the bath temperature, and that's a standard thermodynamics. But if now this coupling is not negligible, there will be some correction here, and computing this trace is actually very. If you don't neglect the coupling, computing this trace is actually very complicated. But you can at least take some first correction order. And on top of that, we define here, so yeah, it's maybe a bit technical, but we define this quantity, which is called the mean force Hamiltonian, not Gibbs. I will correct that as well. The mean force Hamiltonian, which is, if you want, if you have so yeah, the mean force Gibbs state is yeah, so this has a trace of V of minus beta HSB divided by CSB. Okay, and the idea is that, okay, so we imagine that this state should be of the form like that. Yeah, you have to take that with a lot of yeah. You will have yeah, something prime. Okay, and so what we are interested in is to obtain back this quantity here. So that's why we multiply by Z prime, takes a logarithm and divide by beta. Okay, so this is why we have this all this thing here. And so this Hamiltonian here, again, as I said, so contain in the limit of very weak coupling, when you can neglect yeah, apparently yeah, thank you. When we can neglect the coupling here, in this limit of very weak coupling, this here, this Hamiltonian here will be simply equal to HS, the local Hamiltonian. But when you start to take some in consideration that the coupling is finite, you have some correction, and so this Hamiltonian here will contain the free Hamiltonian plus some contribution coming from the coupling between system and bar. Okay, and so this is a physically motivated Hamiltonian. And you can, so for this reason, you can start to build a thermodynamic framework based on that. So in particular, you will define the mean energy of the system with based on this Hamiltonian. Okay, then how you define heat and work is a bit more tricky, because you have to take into account other consideration. Yeah, I don't want to enter into details, but yeah, this is just to give you an idea of one additional framework. And yeah, if you want to know more, there are also some reference here. All right, and so yeah, and so here I'm just mentioning that some other frameworks that I won't even. Yes. Yeah, sure. It's on my yeah.
Who's asking the question? Oh, that's
Sorry, I just was wondering, when Marco was doing his lecture, he talked about the G, that is the likelihood of the bath interacting with the system.
Sorry.
When Marco gave his lecture, he was talking about the G, that is like what I think you said was the likelihood of the bath interacting with the system. How is that related to, is that the same as coupling?
Marco was talking about G, which
There's the G Ks, yeah, that come into the spectral density. Was the G at yeah, the coupling between the bath modes and the system.
Yeah,
But now is that the same as your strong coupling, or is this a no,
I would have to look at the notes of
Okay,
Marco, but I
okay.
think this is not the same.
Okay.
This is an operator, and in Marco's, from what you said, it's in Marco's talk, it was I don't know, function or complex
No.
number.
no,
No?
yeah, I think it was.
I don't know. Yeah,
Okay, okay, I'll ask you afterwards, thanks.
yeah, yeah. We can look. Look at that in more detail. Okay, so yeah, there are additional frameworks. So, for instance, some framework separating the role of the coherence in the separation of what's heat, what's work. So yeah, here are some reference. There's also some framework describing the work as an operator. There are many papers on that. Here I put two references. There's also this question of fluctuation that I might also talk a little bit about if I have time. We'll see. Yeah, and there might be also even other framework that I forgot or I even maybe don't know. So yeah. But so maybe to recap, some main point is that so heat is for quantum system is intimately related to the interaction with external degrees of freedom, whether this is just a small system or a small quantum system, or whether it forms an entire infinite bath, and which is also related to change of entropy. And by contrast, or I don't know, by opposition, the work is related to classical control, or we saw also this example of the laser. It could be also when you treat a quantum system in a semi-classical limit, and it's also related to energy exchange associated to unitary transformation. But yeah, one also important point to keep in mind that for weak coupling and infinite bath, all these frameworks that I mentioned, they all converge to the definition we saw in the beginning of the lecture, which is that the heat is so yeah, here I put finite quantity, so the heat is the integral of this quantity here, which is the rate of variation of the energy due to change in the state of the system, and the work is the other way around, is a change of energy associated to change in the Hamiltonian. Okay, and so for strong coupling, we also saw that the interaction energy has to come into the picture, and how it is taken into account. This will depend on the framework. So with so many possibilities. And for the finite bath also, it's for finite bath, yeah, the evolution, how the state of the bath change has also to be taken into account. And again, this will depend on which framework. So maybe you would ask, oh, okay, well, so now what's the best framework? Or at least the more accurate? That's a good question. We still don't know. It's quite debated. And most probable that the actual real or better answer, this would depend on the context and on what you really want to do when you are manipulating this concept. What is the aim of your operation? Right, and here I put a small recap on the more the dissipative part, but this is I don't need to mention that. This is I mean what Marco explained us, and will continue to explain us tomorrow. Okay, so is there any question? Yeah. Yeah, you need Where's the mic? Water.
Yes, Actually, maybe I can check on the papers. I would love to see how does the Q of t and W of t look like as a function of time, because these are functions, right?
Ah, yeah, here.
Yeah, yes.
Yeah, so this will depend on each situation, meaning what's your system of interest, what the coupling with the bath. Yeah.
Yes, and also that means for any system path coupling model,
Yeah.
one can actually calculate this thermodynamics
Yeah,
quantities. And also, how can one also check if for my model is the thermodynamics laws satisfied? I mean, what are the restrictions between the Q and W?
Yeah, yeah, those are a good question. So yeah, this quantity you can, if you have a definite model for your system, for your bath, you can surely compute those quantities here. At least, I mean, maybe analytically it might be challenging, but numerically, you can, at least if your system is not too big, so it can be a qubit, it can be a couple of qubits, but if you start having, I don't know, 50 qubits, yeah, you would need a quantum computer for that. And also if it's harmonic oscillator, 1, 2 harmonic oscillator, you can do that. If it's more than that, it would be also challenging. But yeah, depending, in weak, at least in the weak coupling situation, I would say most of the time you can end up with analytical expression. And if really it's problematic, you can maybe end up having some approximation, but yeah. And the other question, how you can check that this thermodynamic quantity are the right one? So, I mean, I guess this was more or less your question. I would say you cannot really say. I mean, those are the definition, and you apply this definition. Again, in weak coupling, really, like, yeah, there is a large consensus on those definition. The question is, yeah, when you start to go through strong coupling, yeah, I show many possible solution, and yeah, again, who is the best? It's difficult to say. But yeah, what you can do is yeah, you compute those quantity and you see if according to, I don't know, the intuition you have, the physical intuition you have of your problem, whether those quantity makes sense. But and maybe last one comment that I didn't mention too much for now is that you can also define what's called the entropy production, and those quantity must satisfy so that the entropy production is positive, okay, which is also another way of showing that this defining this quantity makes sense, okay, because they would satisfy a definition of the second law of thermodynamics. Any other question? Yeah.
Can you, I know that it was a question yesterday, but can you just say again in the definition of Q and W, are the rho and H, are they system Hamiltonian and density matrices, or?
Yeah, so yeah, they are. Yeah.
Why is there no bath? So if you had a thermal bath,
yeah,
then isn't there, why is there no heat from the thermal bath? Where's that contribution?
So here, yeah, is maybe, yeah, in the version of the note I will send, maybe I will add index S everywhere and do that now actually.
Oh, so that's the heat in the system.
Yeah.
Oh, okay.
So this, yeah, maybe would help to avoid confusion. Because yeah, unless, I mean, only for maybe the one of the framework I mentioned, all of the framework and there's also the initial considerations are focusing on your system of interest. So what you are describing as heat, as work is always related to this system of interest. That's why I didn't bother putting index, but for the whole nodes, Q and W is for the system of interest. Okay, and yeah. And there's, yeah, only this one framework I mentioned, but then I put the index A and B to distinguish which one we're talking about. Okay.
Thank you.
But now, yeah, in maybe I can complete the comment with this observation. Now, if you come up with the description of your dynamics in this form, as I said, so yeah, as I said, this operator which appears here, which so describes the dynamics, the unitary part of your dynamics, might be different from your local Hamiltonian describing your microscopic model. Okay, so now the question, maybe that was also the origin of your question, which one of both should I take? And so what I'm saying is that for weak coupling, the correction to this guy would be very small. So you can always take the original one, the one you put in the microscopic description of your model. And now, if you go to strong coupling, then this is what we just said. There's many possible options. One option would be to put the operator appearing here, bearing in mind that you have actually many ways of choosing this operator if you make this change in your jump operator. So maybe what you should choose is to consider the minimal dissipator and the associated unitary operator of that. Okay. Yeah. Yes. The mic.
So what is the reason for choosing the minimal dissipator?
Uh,
I guess physical reason. Mathematically, it's kind of nice, but
It's a very good question, and this is something which is missing in the paper. I mean, yeah, maybe one part of the answer would be, okay, so you define a norm, so you could say, okay, I can take the largest the dissipator of largest norm or the dissipator of minimal norm. You could also take any other one, that's true. But if you take the largest norm, actually you can show that you can always, let's say, absorb the unitary part in the dissipator. So if you take the maximal norm, you will always end up with a master equation of this form with no unitary part, and then it means you are Hamiltonian describing your energy is zero, so your system has no energy, so there's no heat, there's no work, and yeah, nothing interesting. So you choosing the dissipator of largest norm doesn't seem to be the right choice. So they say, okay, we will take the minimal. But it's I mean, for me, this is the main weakness of this work, is that it starts, let's say, nicely, because I'm happy to say, okay, yeah, the operator appearing here really have a physical meaning. But then you realize, oh, actually, it is not unique. So I will choose the one as it's to the minimal dissipator, and there's no physical reason for that. Again, mathematically, it's nice, but why physically this should be the right choice. That's very good questions. I don't know. Yeah, any more questions? Okay, so if not, we can start the it's almost ending. We can start the second lecture, which is even longer. Yeah, sorry. Yeah.
So it's related to the initial equation about the strong coupling and the
Yeah.
weak coupling. So I think they were referring to on your phi equation, you had the third term, the chi term, where you had a decay. Yeah, so that decay, you said if it's D0 of T0, then it's like weak coupling or there's no interaction. Yes, I think that question it is something about, I was clarifying the question, which I'm interested in also of the answer. Yeah, if that strong coupling that he's referring to, is it the same decay function that you were talking about?
But so
Is
you're
it the same
commenting on his question?
So the question was, is the
Yeah.
coupling that you are talking about here?
Yeah, it's the coupling between the system and the bath. Yeah.
Yes. Is it the same decay that you were referring to on your previous lecture? That decay term, I'm not sure if.
Yeah, maybe I can, yeah, so the
It's related, but yeah.
Yes, is it the same thing?
When you write down in your model that you were looking at, you write down Hamiltonian in the interaction part, you have these constants G and K.
Yes.
Yeah, so those constants determine
How
strongly your system comes
yes.
to the bar. So yeah, how the overall magnitude of those sense determines
Yes.
whether well you can when you define spectral density, you can kind of incorporate. You can define some parameter which in a sense measures
the strength of the coupling.
The magnitude. And if that parameter is large, that can be very strong. Yeah, but yeah, those constants are related to the strength.
Oh, okay.
Yeah. It's not exactly the same, but it's related. The stronger the coupling, the larger the decaying rate. Yeah.
Just one last question.
Yeah.
It's related to the example that you did for, I think when you had one path.
Yeah. Yeah. Okay.
Yeah,
The
so-
semi-classical limit.
Yes, I just want to understand because you also use the assumption of uncorrelated initial state.
Yeah.
So I thought we use that when we have a very big path. I'm not sure what's the physical motivation of using that.
So yeah, maybe you refers to when you derive master equation. At some stage you do this you neglect the correlation between system and bath, which correspond to the Markovian or is associated to the Markovian approximation. So here we are even, I mean, we are stronger than that. I mean, what we do is a stronger approximation because in the derivation of the master equation, we'll do this approximation, but only at the second order.
Yes,
You will have, so you will expand that, look like an iteration, you will have a first order, a second order, and you will do this approximation only in the second order. If you do this approximation at the first order, what I wrote, what you obtain is a unitary dynamics with a time-dependent contribution, which is generated by the local dynamics, free dynamics of your system B. Okay. And so yeah, again, for an intense laser, this is a good approximation of the dynamics. Now, if you want to describe a dissipative dynamics and you obtain a unitary operation, you say, oh, my approximation was too strong and I have to do more work. Okay. Which means, yeah, you go to the second order and yeah, that's what we do in usual master equation derivation. Yeah, yeah, take the mic. The question should also include the time for the travel of the mic.
Can you understand, like, can you think of work as being the modes of the bath that are resonant with the system, or, and then
Can
heat
you understand the work as being again?
the modes of the bath that are resonant with the system, or?
The system and the bath
So
are resonant.
So the modes in the bath that are
Yeah.
resonant with the system, that would be work, and then the rest would be heat. So they're useful modes in some way.
Yeah, yeah, oh, that's a good question. It's yeah, that's a good question. Maybe there's also this. I mean, this could also enter into the game, I would say. Like thinking of the question of Ahsan yesterday. So what if you take so qubit two-level system in an excited state which is emitting in a single mode? Okay, what is the heat? What is the work? So I said, yeah, I mean, I can do the computation like that, but I would suspect that there is a strong part of the energy exchange which would be work. But yes, that's actually an interesting problem. We started to look at that, and I don't remember why either we find a solution, either not. But yeah, I don't remember what happened exactly. But now, yeah, we could add on top of that what happened when the qubit is resonant or not resonant with the mode, and this might probably also affect how the energy exchange is split between work and heat. So yeah, that's a good point as well. Yeah, it's a mic.
I was going to make a comment on your question. I think it's a good point, and I think that there's probably a lot of truth in that. So something that my group has looked at recently has been this reaction coordinate mapping, and where you bring an effective mode in the environment into an enlarged system, and then that effective mode is essentially treated more like work than like heat, and what's left over in the residual environment then defines the heat in strong coupling regimes. Yeah. So I don't know how it relates to this formalism, but perhaps it could have a similar interpretation.
Yeah, thank you. More questions? Okay, so if not, we start second lecture. So yeah, I will yeah. So the second lecture, there are actually many things I wanted to discuss. I will already see that I will skip some of it, at least some details. And so these many things was first to mention, so maybe the simplest quantum cycle we can think about, which is a quantum heat engine for a two-level system for qubits. Then discuss the question of the irreversibility and the entropy production that I mentioned sometimes already, and then we can really come back on that. Mention also the stochastic version of that, which I think it's quite interesting. And yeah, maybe the plan was to then at least quickly mention the quantum Carnot engine, which is like a refinement or optimization of this quantum auto engine. And then, yeah, some question around the quantum advantage. And finally, one experimental implementation of autonomous refrigerator, quite interesting. and maybe if we have time, yeah, I would show something around how to compute the work cost of quantum measurement and how the work you spend is related to the quality of your measurement, if you want. Okay, so big program. I can already see that lecture 3, I think we can forget about it. Yeah, but let's start with the quantum heat engine. I will go, yeah, a bit, I mean, without too much details. Quantum auto engine, sorry. So yeah, to make it simple, you can generalize that to other kind of system, but to make it simple, I choose a qubits, and oops, and for yeah, for practical purpose, maybe, I mean, if it helps you to have a practical realization in mind, you can think of a spin 1/2. This is the system we commented also yesterday. And so applying work or extracting work for the system will correspond to increase or decrease the amplitude of the magnetic field you apply on that spin. Okay, and for simplicity also, I will choose the ground state of the, I will fix the ground state of the energy ground state of this qubit as 0, which means that, yeah, the Hamiltonian as simply as this form here. Okay, we can do it with the, let's say, the more standard Hamiltonian for spin. But yeah, this is even simpler with that. So yeah, we think that's a good choice. And so the notation is so yeah, maybe also something it's good to highlight is that here again, I mean, all the equation will be about the qubit, the spin 1/2. So I don't put any index, but yeah, everything is about refers, all quantity refers to, all operator refers to this qubit. Okay, so this is the thermal state of this qubit at a given temperature beta here, and with a given frequency or energy splitting omega here, which appears here in the Hamiltonian here. Okay, and Z is again the partition function, which is which you can see at as a normalization factor. Okay, and so if we express now this thermal state in the basis EG, excited ground state, you obtain this explicit form here for the thermal state. Okay, and so the Otto cycle, it's a cycle of 4 strokes, inspired by the classical Otto cycle that you might not know, but it doesn't really matter. And so the initial state of the cycle is a thermal state at a given inverse temperature beta C here, and yeah, here, okay. And yeah, and there's a given energy splitting omega C here, yeah, initially chosen. Okay, and again, here's this pink, this purple sphere here represents the population or the probability to be in the ground state and the probability to be in the excited state. So here, if we come back to this expression here, you see that the probability to be in the excited state is that one, while the probability to be in the ground state is only this one here. Okay, yeah. So you see that due to this exponential factor, the probability to be in the excited state is much smaller. And that's why I put a very small sphere and here a larger sphere. Okay, and this is also it's also, yeah, what yeah, you can think of the ratio of the size of the sphere. It's aimed to be proportional to that factor, right? I mean, even though I didn't make any measurement, obviously, but yeah, that's the idea. Okay, and so the first stroke is to increase to increase the intensity of the magnetic field, which will result in increasing the energy splitting between the ground state and the excited state. And so during this stroke, the spins or qubits receive work. So applied work is positive. Okay, which makes sense since we are increasing the energy splitting. All right, the second stroke now is we switch on the interaction with the bath. So yeah, the first stroke, we assume that there were no coupling with the bath, or if you think about an experimental implementation, you will increase the intensity of the magnetic field on a time scale much smaller than the interaction time scale with the bath, with the dissipation time scale induced by the bath. And so if you do that very quickly, from the point of view of your qubit, is as if you did a unitary operation, and yeah. So then comes either you switch on the interaction with the bath, either it was already switched on, but you did your increase of the intensity of the magnetic field very quickly. And then you have, so yeah, interaction with the bath at a given temperature TH, so H as a hot. Okay, and this will result in, so first, it means that the bath will provide heat to your qubits. The temperature of the qubit will increase and will ultimately thermalize, your qubit will ultimately thermalize with your hot bath. And as a result, the excited population here will increase. Okay, if you go back here to the expression of the excited population, when you increase the temperature, it means that beta, which is the inverse temperature, decrease. So this exponential term here, the argument decrease, so the exponential term with the minus sign increase. Okay, so when you get hotter, you have an increase of the excited population. All right, the third stroke is now to apply the, let's say, the inverse of the first one, which now we decrease back against the intensity of the magnetic field applied to your qubit. And so this time work is extracted from the qubit. We are decreasing the energy splitting. Again, this is done on a very short time scale, or if you want to switch off the interaction with the bath. And the final stroke is to interact, to make your qubit interacting with a cold bath. Okay, and so similarly as the interaction with the hot bath, the temperature of your qubit now will decrease and will ultimately thermalize with the cold bath. And so now if you decrease the temperature, it means that you increase the inverse temperature, which means that you decrease the excited population. Okay, and you arrived at the thermal state at the temperature of the cold bath, which was precisely our initial state. Okay, so we close the cycle and we can do it again and again and again forever. Okay. Now, obviously, the main question is we want to do that not only for entertainment, but because the aim is to extract work. And so how we can see from this scheme that we indeed extract work. It's actually quite simple, so that's why I present this Otto cycle with the qubit. It's because the two, it's also the good thing of the Otto cycle, because in the Otto cycle, it's either a unitary transformation, which will involve only work, either a dissipative dynamics with no change of the Hamiltonian, and therefore which will involve only heat. And so, yeah, for each stroke, there's only, it's either exchange of work, either exchange of heat. And so, yeah, the two strokes which involves exchange of work is the first stroke and the third stroke, which are the strokes where we act on the energy splitting of the qubit. And so the first stroke, we are injecting work in the qubit. And the second stroke, we are extracting work from the qubit. Or if you want, it's a qubit which is providing work to our external drive. And so the aim, yeah, the aim is not to, so yeah, the sum of, I mean, at the end of the day, the work that we extract or that we provide is the sum of W1 and W2, and W3, sorry. And so if the work that we provide to the qubit is larger than the work that we extract from the qubit, after one cycle, it means that we provide more energy to the qubit than we extracted. And so it means that we didn't, after one cycle, we didn't generate work, we didn't extracted work, we provided work to the qubit and ultimately actually to the bar. So to make sure that we really extract work, it means that this stroke here where we are extracting work, the extracted work has to be larger than the work provided to the qubit. And it happens that in this simple configuration, the work is simply given by how much you change the energy splitting multiplied by the excited population. So if you want the work W1 will be equal to the excited population, I would put a 1 here for the first stroke. Yes, sorry, for the first stroke. Multiply by so not to make mistake of sign. Multiply by the final energy splitting minus the initial energy splitting. While the work for the work exchange during the third stroke will be the excited population in during this third stroke minus the final energy splitting, sorry, times the final energy splitting minus the original one. Okay, and so you see that, I mean, graphically that, yeah, we choose omega H larger than omega C. So this quantity here is always positive, which indeed means that we are providing work to the qubit, and this quantity here is indeed negative, which means that we are extracting work from the qubit. And so, yeah, you can recognize that these two factors are the same. So at the end of the day, if you want W1 plus W3, it's simply, I'm gonna write it like that. The excited population during the first stroke minus the excited population during the third strokes time the energy difference. Okay, and so we want, if this is positive, it means that overall we provided work to the qubit. And if it's negative, it means that overall we extracted work. So what we want is to extract work. So we want that to be negative. Okay, which means that this is positive, as we can see graphically, the energy splitting omega h is larger than the energy splitting omega c. And so in order to that to be negative, it means that this term now has to begin, this term here must be negative, which means that the excited population during the third stroke has to be larger than the excited population in the second stroke. And we can see that now if we come back to the slide, we can see that graphically, it is indeed the case here. The excited population we have in the third stroke is larger, the size of the sphere is larger than the one we have during the first stroke. And this is indeed due to the fact that we, between increasing and decreasing, we made the qubit interacting with the hot bath, which increase the excited population. So the aim of making the interaction with the hot bath is precisely to increase the excited population so that when I decrease the energy splitting to extract work, I end up extracting more work that I initially injected in the first place. Okay, so that's how sorry, a quantum auto engine operates. And yeah, from there we can now make some more precise description, which is what comes next. But maybe I will stop here. But I think the tomorrow or the next lecture I will skip these details, which you can go through it in the notes. It's a bit long. But what you obtain in the end is that if you compute what we usually do when you have a heat engine is we want to know what's the efficiency and what's the extracted work per cycle. And the efficiency, so the efficiency is computed as for classical thermodynamics, as for even for maybe some other consideration, meaning it's always what you want divided by what it costs you. So here what we want is extracted work. So it's why I put here the absolute value of the sum of W1 plus W2, and what it costs me, it's the heat injected by the hot bath. Okay, and so if you go through all the math that I skipped, what you obtain is finally this expression, very, very simple, 1 minus the ratio of the cold by the hot, omega c divided by omega h. Okay, the two energy splitting which appears in the cycle we just described. And this is, precisely what's called the auto efficiency, which is also exactly the same efficiency you will obtain if you have a classical auto cycle. So one interesting conclusion is, although we are talking about a quantum system, a qubit, very, very small system and fundamental quantum system, you end up having exactly the same efficiency as if you consider an auto cycle, which was originally designed for big classical system involving large quantity of very large quantity of molecule in a gas and something like that. So, which is so quite interesting that, yeah, even though we are in a scale totally different, even though the underlying dynamics in physics of law are not the same, the efficiency is still the same. So, which is something quite interesting with thermodynamics. Okay, maybe as a last comment, on the other side, it might be a little bit disappointing because you could think, oh, now we have a quantum system. You would hope to have something better, but you don't have. But we'll see next time what we can do if you want something better. Okay, so yeah, I'll stop here and we'll continue next time. Yeah. Is there any question? Yeah, otherwise we can chat yeah, during lunch or afterwards or yeah.
So yeah, need this finish by saying thanks. Thanks, Marco. So to that is also just to mention to everybody, please make sure that you sign the registration form outside if you haven't got it this morning. So otherwise
All right, there you go. Let's have a look at that. There we go. Okay, great. Let me just see, just speaking to one. Hello, hello. Give that one to the speaker. Okay, cool. Thanks, great.
It's your
Oh. Let me help you.
Shows you how often so
There you go.
I was trying to do it the other way.
There we go.
Thank you.
I'll just ask you to count to three, because I was wondering if you test your audio at the back.
Do you want me to join the Zoom?
yeah.
1, 2, 3.
Let's try and log into Zoom.
Should I join the Zoom, Greg?
Yeah, if possible. You know, you still have the link.
You know what you,
I think it's still in.
just plug it in, just plug HDMI in. So there's just a little bit of, rather plug it in this time.
Okay.
I'll tell you why, because the main system, you might be an issue with our Zoom in a few minutes time, because Francesca needs to hop on another one. So
should I not join this then?
you know, you can join, but if it kicks you out, rather join, it's fine. You're already there. Join it, screen share, and if we drop, then we'll switch to the plug.
Okay.
All right.
We have the you have the HDMI cable. So
Is it this?
I'm assuming that one, yeah. I don't think it's this.
It'd be good to go when you guys are ready.
Shall we start?
Yeah, I think we could start.
You ready? Yeah.
Yes.
Okay. Well, welcome back everyone after lunch. I hope you enjoyed the break. I certainly feel like I'm getting well fed while I'm here, which is good. So I hope you're ready for some more interpretations of quantum mechanics now with full bellies. So as we said last time, these lectures, well, this is the second lecture, obviously, are aiming to look at some of the strengths and weaknesses of different interpretations of quantum mechanics and identify some of the tensions between quantum mechanics and relativity, particularly associated with entanglement and non-locality. And we're going to talk about that in a bit more detail today. So the lecture today will maybe be a bit more quantitative than the first lecture. We'll go through a little bit more of the mathematical description of some of the issues we're going to raise, in particular with respect to Einstein-Podolsky-Rosen paradox, as it's known, and also Bell's inequalities. And then we'll see how far we get, whether we get on to the third topic or not. Maybe before I start, are there any questions still left from the lecture yesterday that anyone wanted to raise? We had a few at the time, but just in case there was anything. No? Okay. So if you remember, last time we went through the postulates of quantum mechanics, and we talked primarily about what kind of interpretational issues these postulates raise. And then we discussed a sort of family of interpretations that is broadly known as the Copenhagen interpretation, both older and newer forms, and a sort of very brief amount on a more modern approach termed quantum Bayesianism, or cubism for short. This time, we're going to look in detail at the EPR paradox, and that then motivates the study of Bell inequalities. And particularly that highlights non-locality and the notion of realism within the theory. And we're going to define precisely what these terms mean in the present context. This raises the issue of potentially hidden variables within the quantum mechanical formalism, and we're going to then describe one prominent hidden variable theory that's known as de Broglie-Bohm theory, or Bohmian mechanics sometimes, or also sometimes pilot wave theory. So just to summarize from last time, we said quantum mechanics can be described adequately by 5 postulates. And as we know, they work very well on a practical level. If we don't look too deeply into what those postulates really mean, we can calculate properties of quantum mechanical systems that are testable to a very high accuracy. The Copenhagen interpretation actually embraces a fairly pragmatic view of quantum mechanics. It doesn't necessarily assign any reality to the quantum mechanical world, particularly in the older Copenhagen interpretation. And in the newer interpretation, it assigns some kind of reality to that world, but still associates the quantum state with a state of knowledge about the system rather than an inherent property of the system in of itself. There are no hidden variables within the Copenhagen interpretation. And as I said, it's epistemic. The quantum state is an expression of our knowledge. Remember, epistemic says it's an expression of our state of knowledge, and ontic would be the opposite, where the quantum state would be an element of reality, but it's epistemic within the Copenhagen interpretation. Okay, so for the second topic we're going to look at, we're going to discuss Einstein-Podolsky-Rosen in a bit more detail. So we'll talk a little bit about Einstein and his views on quantum mechanics. That will lead us on to EPR. So EPR as in Einstein-Podolsky-Rosen, and what's termed the completeness of quantum mechanics, which we'll define. So really this is about whether there's an element within the theory that corresponds to every element of reality. And if there is, then quantum mechanics would be termed complete by Einstein, Podolsky and Rosen's definitions. And if not, then it would be termed incomplete. And if it's incomplete, it might need to be supplemented by something, and that could be some hidden variables. And that's what we'll come on into in part 3. We'll go through the EPR argument, actually a version of the EPR argument due to Bohm, so the same Bohm who is the inventor of Bohmian mechanics. So Bohm wrote a quantum mechanics textbook because he wanted to understand what quantum mechanics is. So if you want a deep understanding of quantum mechanics, just go ahead and write a textbook on the subject. The study of EPR leads us naturally onto Bell's theorem and the notion of non-locality, and that will be the next part of this topic, and then finally Bohmian mechanics. So Einstein was a prominent critic of the Copenhagen viewpoint of quantum mechanics. He didn't believe in the idea of leaving the quantum mechanical world somewhat kind of undefined or unreal. He wanted to assign a level of reality to all physical systems. And this was made clear, for example, within the Bohr-Einstein debates, and it's quite interesting to look up some of the history, and you can find many different articles, particularly online, about that. So as I said, Bohr rejected the notion of an underlying quantum reality, which we discussed yesterday. But Einstein didn't really accept that you can't assign a well-defined property to quantum objects independent of measurement. So he wanted to be able to assign a position or a spin or some kind of energy state or whatever property it was to a quantum object, independent of whether that object had been measured or not. So it had been observed to have that property. So it would then exist independent of the act of observation. And a famous quote of his is, "Do you really think the moon isn't there if you aren't looking at it?" So his idea was that the properties were inherent to the object and they were there and defined regardless of whether one was trying to measure them or not. No, it shouldn't be confused with the uncertainty principle. So there's a little bit of confusion sometimes in the literature because Einstein wasn't that happy with the uncertainty principle when it first was formulated. But actually, by the time of EPR, he was completely happy with the uncertainty principle. So it's not an uncertainty principle argument. It's more about the nature of the reality of quantum properties themselves. So the question we're asking really is whether the measuring process brings properties into being or if they exist independent of measurement. So they exist anyway, even if we're not trying to observe the system. So Einstein actually believed that he had an argument, quite a clever argument, as we'll go through, that established the reality of quantum properties. But also, on the other hand, the quantum mechanics doesn't satisfy the full requirements of an acceptable physical theory. And by that, he meant that it's not complete. So he thought an acceptable physical theory has to have an element within the theory that corresponds to any observable property of the system, any real property of the system, I should say more accurately. Is it possible to move that little? I don't know where the. Can I move it on my? I don't think I can.
Yeah, that's the screen. Yeah.
Can it be moved maybe on that?
I don't want to touch anything.
It goes up. It's very temperamental. It's all right. We can carry on for now. Okay, so what we were saying. So yes, so yeah, just to recap then, Einstein said, or he thought that he had an argument to establish the reality of quantum properties, so that quantum properties exist independent of whether one is trying to measure them or not, but that there's not an element of the theory for every element of reality by that definition. And so quantum mechanics is not complete. And by association, then it's not an acceptable physical theory. An EPR argument places importance on what's termed reality, locality, and completeness. So let's define those different concepts. So reality
is defined in the following way. So a physical quantity whose value can be predicted with certainty, importantly without disturbing the system, is a real property of a physical system. So if we can determine it, but without disturbing that system in the process of determining it, then it's defined as a real property of the system. So in that sense, the system owns this property independent of measurement, and that makes it, for APR, an element of physical reality. So that's how they define reality of physical properties. So the act of measuring it doesn't disturb it, and also the property is real, it's owned by the system. You don't need to measure it in order for it to be brought into being. Thank you.
Sorry about that.
That's all right. So locality. So locality states, or we can state that the result of a measurement on a system A, so imagine we have two systems, they're space-like separated. The result of a measurement on a system A is not influenced by manipulations of other systems B, space-like separated from A. So we don't have any faster than light travel essentially between the two objects. That's a locality argument, and then with realism that we defined previously, sometimes the two together are termed local realism. Beyond just that, system A must be characterizable in terms of its own intrinsic properties, regardless of the properties of system B, and likewise system B must be characterizable in terms of its own intrinsic properties, regardless of any properties of system A, and that's termed separability. So these together form their locality definition. And then completeness is defined such that there must be a corresponding theoretical counterpart for each element of physical reality. So if we've determined that that some property of the system is physically real by our realism definition, then there must be a corresponding theoretical counterpart for that property. So if there isn't, it means quantum mechanics is not complete by these definitions. And then there must exist, in addition to just the quantum state, which defines quantum mechanical systems, some further variables that are termed hidden variables, because for some reason we wouldn't have access to them. We only have access to the quantum state itself, but that doesn't give us a complete description by these definitions. So knowledge of those variables would then allow a complete description. Or that was the assumption of EPR. They didn't actually put forward a candidate for, or any candidates for, those hidden variables themselves. So the argument was set out in this paper. So can quantum mechanical description of physical reality be considered complete? And that was given in 1935. And I'll just go through the logic first before describing in slightly more detail an argument or a discussion that was given by Bohm in terms of entangled spin half particles. So remember we said, so actually if the logic is not completely clear now, hopefully it will become more clear when we go through the example in detail. So we said that a complete theory has an element corresponding to each element of reality. And reality of a physical quantity means the possibility of predicting it with certainty, but importantly, which is why I've put it in bold, without disturbing the system. Now, we also know that in quantum mechanics, for two physical quantities that are described by operators that don't commute with each other, the knowledge of one precludes the knowledge of the other. So that's also an important aspect of the argument. However, if we consider the problem of making predictions about a system on the basis of measurements made on another system, and that on another system is important, that had previously interacted with it, it leads us to the conclusion that both physical quantities are real. So we can make measurements. So imagine we have two particles, we let them interact. they form an entangled state. As I said, we'll go through this in more detail in a moment. Then we separate them far enough that they can't interact with each other. We can make measurements on one particle and get results. Because the state is entangled, we assume we now know with certainty what the property of this particle is, because it has to be the corresponding property for the entangled state of this one. But we haven't directly disturbed this particle by any definitions made in the definitions of locality and realism, because we've only acted on the particle over here, not on the particle whose properties we've inferred. And we can do that for X measurements, Y measurements, or Z measurements. And so we can infer all of X, Y, and Z over here are real because we've measured them without disturbing this system at all. Yet X, Y, and Z don't commute. This is giving a particular example. And so the theory itself doesn't give us elements to tell us simultaneously what all of X, Y, and Z are, even though by the definitions we've given, they're all defined as real by the EPR argument. And that's essentially the argument by which they consider the theory to be incomplete. So let's go through that in a little bit more detail. So this is Bohm's version, which is slightly simpler than the original paper. The original paper was given in terms of position and momentum, which obviously are non-commuting variables, but they're continuous variables. So the discussion is a little bit more complicated than for two state systems like spins. So as I said, in Bohm's 1952 textbook, he presented a simpler argument. And so he considered some system of total spin zero, as depicted schematically at the top there, that decays into two entangled spin half quantum objects. So actually he was considering something like an electron-positron pair that both spin half that then move away from each other after this decay. So A moves to the left as we're looking at the slide, and B moves to the right. And we consider them prepared in this entangled state. So spin up on the left here corresponds to spin down on the right, and spin down on the left corresponding to spin up on the right. So once they're sufficiently far apart so they can't affect each other, we measure the orientation of one spin, say spin A along X, and we find it to be -1/2, for example, in one given run of an experiment. Then we know for sure that B is in the SX state +1/2, because that's the corresponding. So we see if we measure A, which is the first arrow in down, -1/2, the second arrow corresponding to that part of the state is up. And so we know for sure that B is in the SX state +1/2. And so the SX state +1/2 of B is an element of physical reality by the arguments of EPR that we've just given, by the definitions of reality, because we've got a local setup and we've managed to measure the state of B without directly affecting it. So we've not disturbed B at all. We've only made measurements on A, which is space-like separated from B, and assumed individually measurable and controllable. However, SX we chose arbitrarily. We can apply the same reason to SY and SZ and conclude that all three spin components of B are elements of reality. So you can check for yourself, but this entangled state that I've given here, I've deliberately not put any labels on the spin states because it's the same entangled state, regardless of whether you define the spins in X, Y, or Z. So you can do the same experiment, but measuring along Y or Z instead. There's no preferred spatial direction. Spin direction. And so you would conclude then that all three spin components of particle B, the one that's moved to the right, are elements of physical reality by the arguments and the definitions of what that means given by EPR. We've managed to measure with certainty what the spin states of B are in non-commuting spin orientations without disturbing B at all, without making any direct measurements on it. Quantum mechanics states that only one spin component can be determined since the three components don't commute. And so EPR conclude from that quantum mechanics is not complete. It doesn't have an element within the theory that determines all three elements of the physical reality that one sees in this system. So the theory doesn't have elements corresponding to each element of reality. And so they raise the possibility that given that the theory is not complete, perhaps there are some variables that are hidden from us. Are there any questions on that? I mean, it's quite a subtle but clever argument to try and determine the reality, the existence of properties of one particle by measurements on another particle. So you're not directly measuring the particle that you're inferring the reality of the properties of. But of course, there's some kind of counterfactual reasoning going on here. You're saying that if I had measured sigma x, for example, on B, I would have got this outcome, but you're not directly measuring it, obviously, because you don't want to disturb it. And likewise, if I had measured sigma y or if I had measured sigma z, I would have got this outcome. But you never actually do those measurements. And so it's a kind of counterfactual reasoning. And it could be that such reasoning breaks down quantum mechanically. And in fact, we'll see when we talk about contextuality later, one has to be very careful about what kind of statements you make, because the results you get can depend on measurements that are being made on other systems at the same time. And this is what's termed a contextual theory. So this is kind of what Bohr's response was. So actually, this caused quite a lot of, well, rightly, quite a lot of controversy. I think this was the front page even of the May 4th, 1935 issue of the New York Times. Einstein attacks quantum theory. He finds it's not complete even though it's correct. So they claim that he believed the whole description of the physical reality can be provided eventually. I'm not sure whether he did believe that or not, but it was certainly his motivation in trying to attack quantum theory, as they put it here. So Bohr's response was based, so he didn't really, so I guess in kind of typical Bohr fashion, he didn't really respond head on to the criticism from Einstein or the kind of thought experiment that was put across. But his response was more based on his belief that you can only determine physical reality with reference to the experimental setup. So the experimental setup has to be completely determined in order for you to say something about physical reality. And so here, his argument was that the experimental setup is physically different, whether you're measuring spin in Z, spin in X, or spin in Y. And so the theory then is accounting for the fact that the setup is different, and one shouldn't make these kind of counterfactual statements that I would have got this result had I measured that, because one has to consider the context in which the measurements were made as well. And we'll talk a bit more about that later, but actually we'll see that contextuality is an inherent feature of quantum mechanics. So probably Bohr was kind of along the right lines here with this response. Actually, Bohr was regarded to have won the argument, but it was thought that it would never be testable. However, Bell in 1964 came up with a testable way to test the assumption that an electron, for example, has definite values for different spin components, regardless of whether one measures them or not. And we'll go on to discuss Bell inequalities now. So let's briefly summarize what we've talked about so far. So Einstein-Podolsky-Rosen put emphasis on reality, locality, and completeness, and we've defined what all three of those are, or at least how EPR defined all those three terms. Within the example of the decay of a spin zero particle into two entangled spin half particles, we showed that all three spin components of particle 2, for example, here on the right, are elements of reality because they can be inferred by measurements on particle 1, which means they're measurements that don't directly disturb particle 2. And so by EPR's definitions, they're then elements of physical reality. However, quantum mechanics states that only one spin component can be determined since the three components don't commute. And so EPR conclude that quantum mechanics is not complete. And then the question that was left after EPR was whether this could actually be tested. And that's what we'll come on to now. Are there any questions before we move on to Bell's inequalities? No? Okay. So next we're going to discuss Bell's theorem and the notion of non-locality, and in what sense Bell's theorem asserts that quantum mechanics is a non-local theory. So in order to do that, we'll have to discuss Bell's inequality. We'll then bring together an EPR-like experimental setup and discuss Bell's inequality violations in such a setup. Actually, I've forgotten to remove that last point. So there's another non-locality argument that was given by Lucian Hardy. That's quite a nice argument, but I've actually taken it out of the talk just to keep things more focused. So ignore that last bullet point. So Bell considered an EPR-like setup again. So spin zero, for example, particle that decays into two spin half particles. It could be, as we discussed in Bohm's discussion of EPR. And he was interested in local hidden variable theories. So Bell wanted to understand what kind of constraints would have to be put on hidden variable theories in order for them to be compatible with quantum mechanics. I'm going to follow an argument here that's put forward by Harrison in this paper in American Journal of Physics. And it's quite a nice paper, actually, and it's quite a neat argument on deriving Bell's inequalities. So I encourage you to have a look at it. Maybe I could include it with the slides or something like that. Yeah. So the setup we're going to consider is a Stern-Gerlach-like apparatus again, but this time it has three possible settings. Well, I guess it had three possible settings last time as well, but it's not X, Y, and Z this time. It's oriented along Z, and we'll call that setting A. So that means we're making measurements in the Z spin basis. C is going to be in the X direction at 90 degrees to the Z direction. And then B is oriented at 45 degrees, so between the Z and X directions. Bell's inequality, in a nutshell, tells us that if the way that electrons will go through an orientation is set in advance, so if the electrons hold these properties independent of being measured, and so they go through in a way that is already determined before we try and measure them, then if we repeat this experiment many times, the number that go, if we set A on the left, so Z Stern-Gerlach on the left and 45-degree angle Stern-Gerlach on the right, that would give us number up A, up B. So we say, we make the settings A on the left, B on the right, and then we say how many go through when a measured spin up on the left and spin up on the right. So that's the number up A, comma, up B. So the left spin orientation corresponds to the left-hand particle, and the right one here to the right-hand particle. So the number that go through oriented spin up with setting A on the left and B on the right, plus the number that go through with a measured have orientation spin up with setting B on the left and C on the right, is greater than or equal to the number that would go through with spin up with setting A on the left and setting C on the right. And this is a general inequality. We're gonna derive it from quite general considerations in a moment, but this is not particular to quantum mechanical states. So these can be systems with any kind of binary properties. So it could be classical systems. Well, in fact, this holds for classical systems, but more generally, it holds for any systems in which the orientation is set in advance of the measurement or independent of the measurement. So let's go through a simple argument to show Bell's inequality. So we consider a collection of objects. Like I said, they don't need to be quantum mechanical. They can be classical or quantum mechanical, but they have three binary properties. So that could be spin orientation, as it was on the previous slide, or it could be anything. It could be, you know, they are one color or not one other color. They are in one position or not one other position, or so on. It could be any property where there's two possible values. Here we'll refer to the values as A or not A. So either it has property A or it doesn't have property A. And not having property A is denoted by A bar. Then the object has property B or it doesn't have property B, so B or B bar. And the object has property C or it doesn't have property C, and that's then C or C bar respectively. Importantly, for the argument to work, it has to have a defined value for all three properties always. So it always has a value of A not or not A, B or not B, and C or not C simultaneously. So we can always define them. So this is what we're saying, that if we can define those properties, A or not A, B or not B, and C or not C in advance, without any reference to any measurements, then we can show that Bell's inequality holds. So how do we do that? Well, let's consider on the left-hand side the number that have property A and not B plus the number that have property B and not C. Well, the number that have property A and not B has to be equal to the number that have property A and not B and have C, or plus the number that have property A and not B and don't have property C, because all object has to either have property C or not have property C. It has to be defined. And so the addition of these two terms has to give us back the number that have property A but not property B. And likewise, if we take the number that have property B and not C, that has to be equal to the number with A, B, and not C, plus the number with not A, B, and not C. So that's just taking the left-hand side and adding in explicitly C and not C for the first one, and A and not A for the second one. Now the middle two terms on the upper line, notice that they both have A and not C. And then they have either not B or B. So that's just the number with property A, but the number, but not C. Okay. So that's by the addition of the two middle terms on the upper line. They've both got A and not C, and then they either have B or they don't have B. And so that's just the number with A and not C. And now, because these are numbers, and every object has either one, has a defined A or not A, B or not B, C or not C. All of these numbers are either 0 or greater than 0. They can't be negative. They can't be any that, they can't be a negative number of objects that have these properties, which means that the left-hand side has to be greater than or equal to the number with A and not C, because the number with A and not C is the number with A, not B and C plus the number of not A, B and not C is greater than or equal to 0. So the left-hand side must be greater than or equal to the number with A and not C. Okay, so how does this relate to spins? Well, if we identify A as spin up in the A direction and A bar with spin down in the A direction, and likewise for B and C, it means that we get the inequality, the number with up A and down B plus the number with up B and down C is greater than or equal to the number of up A, down C. Here we're considering collections of individual objects, and we know that although this looks quite a bit like the Bell inequality that I gave on the previous slide, this inequality, notice that this refers to two spins, not to a single spin. So it refers to two objects, the electron-positron pair, for example, rather than just a single electron, where what we've derived so far refers just to the properties of one single entity, where we have a collection of those entities rather than entangled pairs. Okay, we know that if these relate to spins and they're quantum mechanical, however, we can't simultaneously measure probabilities like A up and B down, because they're not compatible variables. The observables don't commute with each other. So we have to extend the argument to an EPR-like pair instead. So as I said, we can't simultaneously measure non-commuting spin observables on a single spin, but in the same way as we inferred properties of spins in the EPR argument by measuring another spin that had interacted with the spin we're interested in, we know that if in some kind of maximally entangled state, if the left spin has properties up A, down B, then the partner properties would be down A, up B. So instead of measuring a single spin, we measure property A on the left spin and property B on the right spin, and then we have to switch. So if we go back, here was number up A, down B, but if we switch to the two spin case, then it's got to be number up A, comma, up B, because measuring up on the right-hand side implies down on the left-hand side. So we have to flip which spin we have. Is that clear? So I'm saying that if we measure up A on the left-hand side, we can measure whichever orientation we want on the right-hand side, so we can get the number of up B on the right-hand side. Then from that, we infer that if it was up B on the right-hand side, it would be down B on the left-hand side, because it's a maximally entangled pair. And so that gives us this number here. And likewise, we do the same thing with this number and with this number, and that gives us than the Bell inequality as given for entangled pairs of spins in the box there. So the only assumptions, or generally thought that the assumptions that have gone into deriving this inequality is that electrons have spin in a given direction, even if we don't measure them. So the spin is a real property of the electron. It's not brought about by measuring them. It exists independent of measurement. We've also assumed locality, so there's no possibility of communication between the two spins when we're doing these measurements. We have kind of assumed something else, which is that our standard logic holds for quantum mechanics as well. But if we put aside that assumption for now, really what we're trying to highlight here is the locality and the reality assumptions, so the local realism assumptions. So what does quantum mechanics say? Does it adhere to a Bell inequality? Well, let's consider again this spin zero state of two entangled particles, as in Bohm's EPR discussion earlier. And we'll let the Z direction define spin axes. So we've got an entangled state with spin up on the left corresponding to spin down on the right, and likewise spin down on the left corresponding to spin up on the right. If we have a Stern-Gerlach setting A, so Z direction for the left spin, if we measure spin up, well, we will measure spin up on the left, we'll get an output up with a probability half simply from that state. We know that the right spin must now be in the state down, because if we've measured up on the left, that corresponds to down on the right. And we get that with a probability half. A spin down in the Z direction corresponds to, a spin up in the X direction corresponds to a superposition of spin up and down in the Z direction as given here. So remember, setting C was spin in the X direction, and as is well known, a spin orientation in the X direction can just be written as an equal superposition of spin up and spin down orientations in the Z direction. So that means that if we measure setting C in the X direction on the right-hand side, we will get up on the right-hand side in that setting with also a probability of half. So the total probability to get spin up setting A on the left and spin up setting C on the right is a quarter. A half times a half. If we repeat that experiment many times, n times, then the number of times we should get spin up with setting A on the left, so that's a Z orientation, and spin up with setting C on the right, that's X orientation, is a quarter times n. Now we can go through the same analysis for the other possibilities. So remember this number, 0.25n, this is up A, up C, is what appears on the right-hand side of the Bell inequality. So the left-hand side should be greater than or equal to 0.25n if our local realism assumptions are correct. If you go through the same analysis, I'll leave that as a kind of homework problem. So that's setting A on the left and setting B on the right. Remember, that's in a kind of superposition between Z and X. And then setting B on the left and setting C on the right. Then we actually find that the sum of the left-hand side numbers equals 0.146n, roughly speaking, which is obviously less than a quarter n. So we can construct states in quantum mechanics that violate Bell's inequality. And actually, this has also been verified experimentally, modulo some potential experimental loopholes that are gradually being closed as more and more sophisticated experiments are being performed. So it seems like quantum mechanics really does behave in this way, and it violates Bell's inequality. So quantum mechanics then can't be explained by any local hidden variable theory. More generally, it's not compatible with local realism. It's not compatible with EPR's criteria and their assumptions. So it's this sense in which Bell's theorem shows quantum mechanics to be non-local. And in particular, what it tells us is that any hidden variable theory, if such a thing exists, the hidden variables have to be non-local as well. So it doesn't tell us that hidden variable theories don't exist. That has been misinterpreted in the literature before. It tells us that local hidden variables are not compatible with quantum mechanics. So as I said, the quantum mechanical violation of Bell's inequality shows that it's incompatible with local hidden variable theories. So either quantum mechanics is complete, or hidden variables are very exotic in their own right. So they need to have influences that appear to travel faster than the speed of light. So it's this sense in which quantum mechanics is non-local, but it still doesn't allow one to exchange information faster than light. So, you know, if you're measuring a property at A and a property at B to see that those measurements are correlated, you still have to come together and communicate the measurement outputs. So you can't use this kind of property to send any information or signals faster than light. Yeah, okay, so if one looks at the left particle, for example, we see probabilistic measurement outcomes. So they don't allow us to infer anything about the settings on the right. We don't know necessarily what orientation of Stern-Gerlach has been set on the right. And so we can't then infer what the state is on the right-hand side. We would only be able to do that once we communicated those settings between the two parties. Well, I kind of just said this. So yeah, just to reiterate, quantum mechanics is incompatible with local hidden variable theories. And this is the sense in which Bell's inequality tells us that quantum mechanics. So we're going to go on to a hidden variable theory in a moment, but I just thought I'd pause there for a moment and ask if there are questions at this point.
So, yeah, does it mean that quantum mechanics is non? Yeah, so there's this thing of it's either non-local or not real.
Yeah.
So is it necessarily so that Bell's inequality tells us that quantum mechanics is non-local?
No, it tells us that local realism is not adhered to by quantum mechanics. But if it is real, as in if hidden variables need to be invoked, then they must be non-local. But it could be non-real. And most likely is when we consider things like contextuality that will come later. Okay, so the last part of the second topic is on an example of a hidden variable theory, and it's probably the most well-known hidden variable theory. And this I've termed de Broglie-Bohm or pilot wave theory, sometimes just known as Bohmian mechanics, although David Bohm's formalism built on work that was put forward by Louis de Broglie as well, although actually I'm not sure that Bohm was necessarily aware of de Broglie's work at the time that he was formulating his pilot wave arguments. So I'll go through an overview of the theory, some basic formulation and simple examples, and then we'll briefly discuss some of the general merits of the theory and criticisms as well. I've called it a theory here because it's usually called a theory in the literature, but actually it doesn't make any predictions that are incompatible with standard formulations of quantum mechanics. So it's not really a theory in that way in its own right, or at least it's not a separate theory to quantum mechanics. Okay, so, well, I already mentioned that there was kind of a couple of ways that pilot wave theory were developed, somewhat independently by de Broglie and Bohm. But the mathematical formulations differ slightly. We'll talk a little bit more about the Bohmian formulation, but in general, it gives the same predictions as conventional quantum mechanics, at least in the non-relativistic regime. You can think about Bohmian mechanics as taking a particle and wave viewpoint rather than a particle or wave viewpoint. So it sees the totality of the quantum description as both particle and wave simultaneously, and that one needs to use both descriptions to get a full description and interpretation of what quantum mechanics I'm not connected to the Zoom now. So we're talking about, we're saying that it takes a particle and wave viewpoint. So the physical system is completely determined by the wave function and the particle positions, and both are considered to be real. And the wave function here plays a dual role. So it evolves according to the time-dependent Schrödinger equation, and that provides a pilot wave, as it's termed, that guides the continuous trajectory of a point particle, and that particle moves through a quantum potential that is provided via the wave function itself. The wave function also tells us the most probable position of the particle through its squared value, its modulus squared value. So this means that Bohmian mechanics provides an ontic interpretation supplemented by a hidden variable. So it's ontic, it assigns a reality to the wave function. The wave function is something that really influences the trajectory of the particle. And so it's a real physical influence. And the hidden variable itself is the actual trajectory of the particle, which is unobservable. And the reason it's unobservable is because measurement is included on an equal footing within the Bohmian mechanical formalism, as in one has to determine what the physical setup is in order to, one has to specify the physical setup in order to determine the subsequent evolution. And so if one tries to isolate as best as you can, localize as best as you can the position of some particle, or to try and monitor it as it's moving through space to track the trajectory, you're looking at a different physical setup as an experiment where you're not constantly monitoring that trajectory. And so in general, it's hidden unless you literally have a setup that measures it, fully, and then the corresponding predictions are going to be completely different to the case where you don't do that. So there's no collapse. We measure particles, not the wave function. So they hit some screen and make some mark, for example, in a 2-slit experiment. And those particles move along well-defined trajectories within the formalism, but they're still not available to us to be seen, so they're unobservable. And the probabilistic character enters then through our ignorance of the hidden variables, and in particular, it's impossible to determine the initial values of the particle positions. As I said, if we were trying to localize as best we can these initial values, then we would have a different measurement setup than just allowing particles, for example, to go through 2 slits that have been prepared in some state that we haven't tried to measure. The theory is highly non-local, and that's because there's an instantaneous influence of the wave function from all positions at the actual trajectory. If the wave function changes somehow at some position, that instantaneously affects every other position within the theory. And we'll see why that is in a little bit more detail in a moment. And perhaps the most important thing about Bohmian mechanics is its historical importance, because it was basically considerations of Bohmian mechanics that led Bell to start thinking about hidden variable theories and to formulate the inequality that we've just been talking about. So even if you don't subscribe or you don't allow any importance to Bohmian mechanics as an interpretation, you should still recognize its importance in terms of its influence on Bell. So we'll just sketch out the formulation. We won't go through it in detail. So the starting point is the usual time-dependent Schrödinger equation. So IH bar d by dt of the wave function is equal to minus p squared over 2m plus v, where v is the usual externally imposed potential, if there is a potential in the problem that you're considering. We define a probability density R, which is the modulus of the solution to the time-dependent Schrödinger equation squared, so mod psi squared. And we'll write psi as R to the half, and then e to the I s over h bar. So we can do that as a kind of decomposition of the wave function in terms of R and S, which are both then real. And so that gives us an arbitrary state just written in terms of two real functions R and S. We can substitute that into the time-dependent Schrödinger equation. And if you go through the derivatives with respect to time and with respect to space, you find that you get both real and imaginary parts on each side of the time-dependent Schrödinger equation that you can then equate, and that gives rise to these two equations here. Now, the first equation is a continuity equation. So it tells us that probability is conserved, so that any change of probability or probability density within a region represented by dr by dt is compensated for by a probability flux, so a flow of probability density out of that region. So it's got a standard form of a continuity. Bye. Okay, the second equation we need to consider in a little bit more detail. So it doesn't have such a straightforward interpretation, but we'll see in a moment the interpretation that Bohm gave to it. So this was the second interpretation in terms of S. So if we look at that equation and take the limit h bar goes to 0 in the final term on the left-hand side, we see that that term vanishes. And h bar goes to 0 is generally thought of as a classical limit. And actually, what we're left with is a formulation of classical mechanics. So if that final term is not present, we have what's known as the Hamilton-Jacobi formulation of classical mechanics, provided that we identify the momentum, which is m times v, so mx dot, as this gradient of s. So then the second term on the left-hand side looks like the usual p squared over 2m kinetic energy term. Now, you might not be familiar with the Hamilton Jacobi formulation of classical mechanics. Certainly, it's not something I've ever studied in detail, but it's another formulation along the lines of the Hamiltonian or the Lagrangian formulation. So it's equivalent, but just set up in a slightly different manner. What's important about that is that Bohm then maintains this identification for h bar not equals to 0. So he says, let's identify the gradient of s with the momentum, so with mx dot, even when h bar is not equal to 0. Then our conservation of probability equation simplifies. So remember on the previous slide, I had this del r dot del s over n, but if del s is identified as the momentum, then that becomes r dot r plus del dot r dot v, and r dot v then is the form of a probability density flux. So it's clear why that is then a continuity equation for the conservation of probability. And then the second equation then looks like a Hamilton-Jacobi equation, but with an extra potential. So this would be the classical version. And then this is now an extra potential, which is the quantum potential, as it's called. And the quantum potential is determined via the formula given in terms of R above.
So I just wanted to ask two questions. Also, I wanted to first ask about the wave function to define later on what is. So I want to understand this, the classical limit to h bar goes to 0. Is it the same as the one we spoke about yesterday when we said, was it a
correspondence? Yeah.
Similar.
So, okay, those are both good questions. So the definition of S is just through how I write the wave function here. So I haven't given an expression for S. That will depend on the problem under consideration, and I'll give two simple examples later on. But otherwise, this is just some kind of convenient rewriting of the wave function or parameterization of the wave function that Bohm used to try and bring out meaning for different parts of the wave function, so to try and interpret what quantum mechanics is telling us. The second question, No, I mean, I don't, there are many ways that people define a classical limit of quantum mechanics, and h bar goes to 0 is one, because then energy levels become very closely spaced, and so they look more like a classical continuum of states. But it's not necessarily the same as the correspondence principal limit. So where does the probability arise in this formalism? So in principle, we can solve the Hamilton-Jacobi equation, so that second equation for S. So if I just go back. So we could solve this equation for, if we know V, which is just set by our initial Hamiltonian in the problem, that's just the potential energy term. And we know W, because we can solve the time-dependent Schrodinger equation, then we can find S from this equation, and then S tells us it predicts the trajectory because the gradient of S is equal to mx dot. And so we can then solve for x. Equivalently, we can just solve directly for x dot as 1 over m gradient of m. Part of the log of the wave function. So we solve the time-dependent Schrodinger equation as usual for a given initial condition, and then use this to solve for the trajectory x subject to whatever initial condition x0 that we take, and then we can get a prediction for the trajectory. So it looks like a completely deterministic theory without probability. But as I said, we don't know the initial position.
Okay.
Okay. Yeah, okay, so we don't know the initial position, as I said, so we can't completely determine the initial position of the system. I mean, the wave packet is going to have some spread. For example, it's not, you know, going to be in a position against state, whatever that means, given the fact that it's a continuous degree of freedom anyway. So the theory then supposes that given an initial wave function, there's a probability distribution of initial positions that is given by the modulus of the initial wave function squared. And then this is a bit more like classical statistical mechanics. The uncertainty arises in the formulation through uncertainty in initial conditions rather than uncertainty in subsequent evolution of the system. Remember, there's no collapse here in this formalism. Measurement is considered in the same on the same level as any other evolution. Because we have a continuity equation, that means that given the initial distribution, the distribution at later times is modulus of psi t squared, and that's in agreement with the Born rule. So we still get the same Born rule out for the probabilities, and so we get the same predictions as standard quantum mechanics, but with a slightly different interpretation of how probability arises. So maybe a couple of simple examples, illustrative. So we can't get much simpler than a free particle in one dimension. So let's start with that. Wave function is given at the top there. It's some plane wave with some appropriate normalization. Let's ignore the fact that we can't really normalize that. Remember from the definition of parameterization of the wave function. I can put it on here. What did we have? We had psi is r to the half e to the I s over h bar. Is that correct? I've not missed any terms out. Yeah. I'm only writing on there because I feel left out that I'm the only person who hasn't used the flip chart yet. So from our definition of parameterization in terms of R and S, we see that for a plane wave, S is equal to h bar kx minus omega t. And so that means x dot. Remember that x dot is 1 over n. Well, the gradient of s in one dimension is ds by dx. So we get that x dot is 1 over m ds by dx, which is just equal to h bar k over m, or over n. And so the solution is simply the trajectory x equals h bar k over mt plus whatever value of x naught we take. And so for free particles, we have simple trajectories that just increase in position linearly with time from various different positions at t0, which would be determined by whatever initial state so the probability of having those initial conditions would be determined by the initial state, the modulus of the initial state squared. We can also look at other situations. So what happens if we look at the ground state of a one-dimensional box? So a 1D potential well, where it's infinite outside and 0 inside of length L. If we do that, we know that the ground state wave function is given in the form that I've given here in terms of a sine function with an exponential time evolution according to the eigenvalue of that state E1. That means that S is equal to minus E1t by this definition. That doesn't depend on position at all, and so x dot is equal to 0, so the particle velocity is 0. So in Bohmian mechanics, what we normally term stationary states literally are stationary states. The particle trajectory is at rest. we won't go through the double slit example in detail, but the way the double slit example is interpreted within Bohmian mechanics is that the particle trajectories go through a double slit. They are going through the left-hand slit. Sorry, if they go through the left-hand slit, they are ending on the left-hand side. And if they go through the right-hand slit, they're ending on the right-hand side. And they do go through either the left or right-hand slit within Bohmian mechanics. The pilot wave, which is the wave function, goes through both. So the trajectories go on well-defined trajectories. The pilot wave is this non-local thing, the wave function that goes through both. And that gives rise to the quantum potential on the other side of the slits, that term W within the evolution equation for S that we had earlier. And that's determining how the trajectories move. And the quantum potential then gives us motion that's highly non-classical. And the trajectories then bunch up around points of constructive interference. The initial positions behind the slit are unknown, and that's why we get, what seems to us to be random measurements of the position that when we repeat the experiment over and over again, that gradually build up this interference pattern. But on any one run of the experiment, according to Bohmian mechanics, the trajectory is well defined, and particles really do go through one slit or the other, not through both at the same time. Of course, if we try to measure which slit they go through, that's a different physical setup to not measuring. And so Bohmian mechanics would give us different predictions, and it would predict that the interference pattern was destroyed as well. So there are some merits of this way of looking at quantum mechanics. One is that, once we defined an initial probability distribution, we have a deterministic description of quantum mechanics that includes measurement, because we have to include the description of the measurement apparatus within our formalism, and there's no wave function collapse. It doesn't assign any special role to an observer, so there's no question of who makes a measurement or whether you have to be conscious to be able to make a measurement, or any of those kind of philosophical considerations. And like I said, it's a physical process. There's no instantaneous collapse in the measurement process. And as I already mentioned, perhaps as importantly as anything else, it inspired Bell to think more deeply about non-locality. There are some important criticisms as well. So Bohmian mechanics yields the same results as conventional non-relativistic quantum mechanics, but to some it's deemed unnecessarily complicated because we need to do more work. We need to solve two equations essentially to determine the evolution, rather than just the standard time-dependent Schrödinger equation. Even once we do that, we can't avoid some counterintuitive phenomena such as non-locality. So we still have to accept that there's a non-local influence of the pilot wave over all space, an instantaneous influence. And it just substitutes statistical uncertainty, or one criticism is that it just substitutes statistical uncertainty in initial conditions for uncertainty in measurement. And so you're just sort of hiding the measurement problem issue within the initial conditions rather than really overcoming it as such. Perhaps most importantly, from a practical perspective, it's not Lorentz invariant, or it's not been made Lorentz invariant yet. And so we can't reconcile Bohmian mechanics yet fully with quantum field theory. So it doesn't give us a Lorentz invariant theory. Okay, just to conclude the final part of the second time. Okay, so de Broglie-Bohm theory provides an ontic interpretation of the quantum state. So the quantum state is a real property of the physical system, and it's supplemented by a hidden variable, which is the particle position or the trajectory. As I said, the probability arises through a lack of knowledge of the initial positions, which can never be completely determined. And there's no instantaneous collapse in the theory and measurement. And well, we've just outlined some of the criticisms. Okay, that was the end of that. I won't go into Hardy's argument now. I guess I should probably stop there, given the time. Is that about right? Yeah. Okay, thanks. Any other questions?
I had one very small question. So when you write down you do that kind of decomposition of the wave function into the real and imaginary parts.
Yeah.
The S is it's written as S because it's the action.
Essentially, yeah.
Okay. Because the wave, it's when I see an I, e to the IS over H bar, then it looks like an action. But it doesn't have any special role, like.
I mean, its role is to give rise to the two different equations. In a sense, what Bohm wanted to get to was equations that he thought he could interpret more physically meaningfully in terms of evolution equations than the time-dependent Schrödinger equation. So the decomposition is important from that perspective because it gives you a probability. A continuity equation of probability density that looks like a classical continuity equation. It relates the flux to the time variation of the probability. And then this other equation that looks like this Hamilton-Jacobi formulation of classical mechanics, but with this extra quantum potential.
But the fact that it's the action, is there any special meaning behind that, or is it maybe there is? But
I don't know. I'm not sure off the top of my head. Yeah, I'd have to think about that a bit more.
Do you want the mic?
Thanks. So thanks. I'm no expert at all in pilot wave theory. The figure on the left there is iconic. I think it was probably in Bohm's book.
Yeah.
Which I did look at many years ago, but so long ago I don't remember. The question is really, what does pilot wave theory say about, for example, things that happen with internal states? What happens with spin and angular momentum? So I've seen these kind of traveling wave solutions, but as soon as you said there is no collapse, that's like a red rag, and I'm thinking, well, hang on, quantum jumps are actually observed with trapped single ions.
So,
and how would a pilot wave theory sort of get to grips with that?
Yeah, so that's a good question, actually. And I think this also arises in things like objective collapse theories as well, that favor measurement of position as the collapse mechanism. There are some arguments in the literature that essentially whenever one makes a measurement of anything, one is making a position measurement, even though you might be inferring a different quantity. So for example, in a Stern-Gerlach apparatus, you make a position measurement and infer a spin state from it. And I think that that's probably how you would have to think about that within the Bohmian mechanics setup as well. But I haven't gone into great detail on how, exactly one would encode spin degrees of freedom within the formulas. So obviously the state space would have to be expanded because the time-dependent Schrödinger equation I wrote down does not have any spin degrees of freedom associated with it.
So you're not aware of anyone adapting it to have?
I'm sure that's been done, yeah, but I think it will, in the end, you will have to relate trajectories again to the system.
Yeah, it's not obvious. I mean, the Stern-Gerlach example is a good one, but it's not obvious how it would work with, say, a setup of collecting fluorescent light from a trapped ion, where the ion's in one spot.
Yeah, I don't know. Yeah. Like I say, you could probably level similar criticisms at objective collapse theories as well.
So would it mean that nobody's ever taken the pilot wave theory, applied it to a Bell's experiment, for example, because then you're dealing with the spins again? And
no, I think you could do that, as I said, through a representation of Stern-Gerlach apparatus. I'm not sure if anyone's tried to do, like you say, spin measurement via a resonance fluorescence experiment. I don't even know how you would start that calculation, to be honest. Perhaps it's out there, but it's not something I'm aware of.
Thanks.
Anything else? No, I guess probably it's coffee time then.
Yeah. About a half hour break to reconvene.
Okay, so maybe we can start. So yeah, welcome back for the last lecture of today's session. So I'll introduce our next speaker since it's his first lecture of the school. So so this is Dr. Neill Lambert. He's currently a senior research scientist at RIKEN in Japan. And he will be talking about QTIP, which is a Python library for simulating, I think, open systems and some, I think, quantum information processing stuff. So anyway, let me hand over to the speaker. Thanks. Cool.
Thank you, Graham, for the introduction. And also, I get the impression Graham has been working incredibly hard for this workshop. So thank you very much for all your effort and the invitation. And also to Bethany, who also emailed me about this summer school. So yeah, as Graham mentioned, I'm going to talk about mostly software for some parts of this, some of these presentations. So alongside the PowerPoint, I made a sort of Python notebook. So if you're interested in looking at some of the code and examples that I show, you can sort of scan this QR code thing with your phone, if anyone cares. And it should take you, I'll just show you, it should take you to, the problem is it's difficult to make short links now, so I tried the UR code instead. It should take you to this sort of Python notebook running on Google Colab. And you can just run some of the code as you go, or later on, if you like. But sorry, I'll go back to the QR code. Yeah, okay. There's a minute. Sorry, I was too quick. From current slide. Here we go. Let me know if it doesn't work because I don't know how to make it. So yeah, so there's also some other resources. So some part of this first talk is about the new release that we did last year, and we wrote a sort of review paper about all the new features and examples and stuff, which is on the archive here. There's like 70 pages with lots of details. So as a sort of resource, I think it's also useful. I should also ask, has anybody used QTIP before? One person, two people, three people. Has anyone not used QTIP? Okay, something between those two. So this is good because my first talk is very much an introduction to the basics of QTIP, but then later on I'll show more complicated examples. And yeah, that's basically it. They have this website, qtip.org, where you can also download lots of tutorials and example notebooks and things. So maybe I should also mention who I am. So I'm from the UK. I'm from Manchester, which is where Ahsan. And I just wanted to mention that Manchester is famous for certain things like graphene, Manchester City football team, and miserable music. And also there's a lot of some good music. There's a Joy Division. This is a good one. And then we have also a big history of Industrial Revolution. As a high school student in Manchester, all you hear about is how great the Industrial Revolution was, like trains and steam engines. So I think this is maybe why Ahsan has to work on thermodynamics. It's like mandatory in Manchester. But then I moved to Japan almost 20 years ago. So I was at the University of Tokyo for a couple of years, and then I've been at RIKEN for ages. And actually right now, it's the cherry blossom season in Japan, and RIKEN campus is one of the best places, I think, to look at cherry blossom, but I'm missing it this time. I just wanted to show you very, very briefly where RIKEN is, because I was talking to some people and they weren't so familiar with it. So this is like central Tokyo over here, and RIKEN is sort of just on the edge of Tokyo. So between this, but it's like a 20-minute train ride into the city center. So if you want to visit, it's a really fun place because you can see all of Tokyo and go to karaoke and these things. And okay, go back here. Okay. So the first part, I'm just going to give a sort of a waffle for a while about the history of QTIP. And part of what I want to say here is about more general things about open source software. I think Francesco mentioned that there is an effort to generate open source software in this network or center they're organizing here. And so maybe I can just give some sort of lessons learned about that process. Then I'll talk about QTIP itself and also the new things in this version 5. So tomorrow I want to use QTIP to sort of, Bethany asked me to give an example from quantum biology. So I wanted to show how in QTIP you can do a sort of basic analysis of something like this light harvesting in photosynthesis, and also use this as a way to introduce more sophisticated system Bath models, particularly what we call this hierarchy equations of motion, which is a feature that we have in QTIP. And then in the last talk, I wanted to show other examples of applications of these, what are called non-Markovian methods. And I'll explain what this means when we get to it. And then more recently, these methods have seen interest in physics. A lot of them actually came from this physical chemistry, quantum biology sort of community. But nowadays they have applications in other topics. And I want to just give a little bit of flavor. And actually, this is a little bit less code and more like a physics seminar. So it'll be a little bit less detailed, but we'll see how we go. So this first part, I asked ChatGPT to generate this image of a physicist programming, and soon to be replaced by ChatGPT itself. I think this is a small thing I wanted to mention during this talk is that particularly is when you're programming for science nowadays, there's everyone's talking about how these large language models are a very useful tool, and maybe you can just code with some vibes, or instead of, I don't know what it means to code with vibes, but you have you don't need to have the detailed technical knowledge, and you can just use the language model to solve the problem for you. I would say these tools are amazing, and they're definitely true. But one thing I want to mention is that we have QTIP on GitHub, and we allow people to do pull requests and like add new features. And this year we've seen a lot of random contributions, obviously generated by these large language models because the spelling is so good, but they don't work. Like literally none of them have worked because the contributors just didn't even run the code themselves. They just asked the language model. The language model doesn't know the details of QTIP. It makes a best guess. And so these things, they're just not working. So certainly you should use these tools. I think they're amazing, but at least it requires a bit more work than just copy pasting what it tells you. Anyways, so I'm going to go through the history a little bit, then give the longest part of this talk is just this sort of main functionality with some little examples. And I guess this sort of builds on what you heard from Marco's presentation and a little bit of Camille's. And then I wanted to, maybe for the expert users, I think there are only 3 or 4, I want to sort of exemplify what's new in this big update we've just done. I want to give a little bit of example of the applications we have towards quantum information. So we have this QTIP QIP package, which is more of a quantum circuit simulator. And I thought I'd squeeze this in here and just waffle a little bit about the future of QTIP development and so on. So the background to this is that there is a large history of people making open source software for quantum physics. And initially this was in the context, I guess, of quantum optics. And there's a very famous toolbox called the Quantum Optics Toolbox, which was written in MATLAB. And when I was a student, I actually used to use Fortran for a while, then I switched to C. And then I actually started using this Quantum Optics Toolbox in MATLAB around 2005. And I think it's really, really, really good. The developer left academia, as far as I understand, which is a theme we'll see very common in this talk of successful software developers leaving academia. But the problem, of course, MATLAB is a expensive piece of software. And at this time, Python was becoming very popular. So around 2011, here in RIKEN in Japan, 2 of our postdocs, Paul Nation and Robert Johansson, who's a bit covered by myself, started developing this Python version of this quantum optics toolbox, essentially. So what they did is they wanted to mirror the functionality of this toolbox into Python, which was this very popular language for data science. And I'm sure if you're doing programming in undergraduate, you probably get exposed to Python nowadays, just simply because it's so popular. And they started this around 2011. Then around the same time, there's a lot of other packages appearing. There's an early one from Google. There's a huge amount in like 5 years ago from various places. Then, of course, companies started appearing because of this second quantum industrial revolution. These companies started investing a lot of money in open source software as a way to attract people to their hardware platforms. So, for example, IBM provide Qiskit, Rigetti were doing stuff, Google had their Circ, and so on. So, on the one hand, this is great because these companies are investing a lot of money, but on the other hand, a lot of these sort of more independent academic packages stopped being maintained, and as soon as open source software stopped being updated, it just stops working. So probably a lot of these early packages are still on the internet, but they have dependencies, and dependencies change, and essentially within a couple of months, a piece of software can be redundant or out of date. So a large problem of open source software is not just making the software, but maintaining it. But in any case, Paul and Rob started this in 2011. And they did like a series of releases. And then, as I mentioned, they started with this mirroring of this MATLAB toolbox. Then they added more and more features like this time-dependent Hamiltonians, block-Redfield solvers, which I will talk about today a little bit. Then they added things like stochastic master equations, an initial version of this QIP module. And then around this, I started getting involved around 2016. I helped contribute this HEOM solver. And another academic from the UK added these optimal control methods. But then Paul and Robert both got much better salaries outside of being a postdoc. And so Paul moved to IBM and Robert became a data scientist in RIKEN in Japan. And there was a sort of weird period of like abandonment. We hit this problem of maintenance. So if you don't continuously maintain the software, it will break. Qtip started to get a bit creaky at the edges. So we had a postdoc, Nathan, and a student, Shanoaz, who sort of made a huge effort around 2018, 2019 to sort of reinvigorate the development of Qtip, make sure it kept working, attract new developers. And we also took on this Eric, who's basically a sort of permanent developer who works in Sherbrooke with Alexandra Blay. And he's one of our most consistent contributors. And so with this sort of new team, we essentially breathe new life into the software. So this was a really sort of a situation where the whole Qtip package may have just been abandoned. But fortunately, because there was a large effort by particularly Nathan, Shanoaz, and Alex and Eric, it could get resurrected. And the other thing we did is we got involved in this Google Summer of Code. So I will advertise this quite a bit because I think this is really, really good. So this is a yearly thing that Google organize where they provide money for students to work on open source software for about 3 months during the summer. And this is like a very large system. I think this year they had 20,000 applicants to the scheme. And every year we've been adopting this Google Summer of Code students. We normally get two per year. And this is a really, really good way, both for open source software to maintain some life and get people contributing things and get involved, but also for students to get paid and also get involved in open source software. So if you're developing an open source package, I would look into getting involved in Google Summer of Code to get people to help out and contribute on it. And if you're a student who really likes programming, I would definitely look into this as a way to, if there's a particular package, doesn't necessarily be Qtip, but there's many, many other packages in data science, machine learning, particularly AI, of course, now is a big thing. So I think Google really likes it if the project involves AI in some form. So it's really, really great. Maybe I can just show the website for this. So just so people, so there's just this website, Google Summer of Code with google.com. The deadline for this year's projects was like yesterday. So, so this year it's too late. But the way it works is you basically you find if you're a student, you sign up here and you find a organization on GitHub who is involved in GSOC. You look at their page and they'll have a bunch of projects that they want people to work on. Then you write basically a proposal and submit it through the Google site. The organizers of the GitHub project then look through all those proposals and they sort of judge them in some way, maybe interview the candidates and pick one or two. And essentially that's the way it works. So it's a bit like also doing your first ever grant proposal. So it's kind of fun from that aspect as well. I should also mention there's a huge uptick in large language model generated proposals as well. So for better or worse, it's there. And I think the money they pay is maybe a few $1,000s for 3 months effort. So I think it's kind of reasonable if you have nothing to do. Okay. Oh, let me go back. So now we have this sort of new admin team, more or less, which is about this number of people. A large fraction of these were former Google Summer of Code projects who just stayed on and kept contributing. Simon was a technical staff we had in RIKEN a couple of years ago. Now he works in Zurich Instruments. He's actually from Cape Town. So he was giving me lots of hints for my visit. I should do this and that and the other. So I don't know if he visits Cape Town, maybe he can drop by here and visit you guys in Stellenbosch. There's Paul, who's a postdoc in RIKEN and also one of the most active developers at the moment. And we also have various people in Ulick, Nazir and Boxy and so on. But this is almost like, these are the official admin team in the sense that they're people who have the ability to merge new contributions to the package. But on top of that, there's just hundreds and hundreds of people who just contribute code. So it's not like a closed system. Essentially, anybody can go on the website, think they have find a bug or add a new feature and just contribute it. So there's no barrier to this process. So I encourage people software just to do it. You don't even have to be in this Google Summer of Code. It can just be some independent thing. And as we did this new version last year, we had a little workshop where we invited everyone to RIKEN and ate lots of food and this kind of thing. And we even had an official logo that my wife drew. So I wanted to say one more thing, just a bit more details on this Google Summer of Code. The total number of projects that we had was about 16, and of those 16 students who completed their projects, I think everyone was basically successful. I think 3 or 4 ended up joining this admin team. In particular, one who I'll come back to at the end of the talk, Jake, was a student in Imperial with I think he was a PhD student with Florian Mintert. And this guy was like a sort of, how to say, it's like a hurricane coming in. There's no part of Qtip code that he didn't change, essentially. So he was almost like the main developer of this new Qtip 5 release, even though it was only a short 3-month project. He ended up doing a huge amount. Now he's essentially retired from Qtip, and he immediately got hired by Paul Nation into IBM Q. So again, this is this feature that if you're good at software and enjoy it and actively contribute to open source projects, it's a good way to get a job, essentially, but not necessarily an academic job. It's a good way to get an industrial job. A bit of self-promotion about the statistics of Qtip. I don't really know what this means, but this is essentially the downloads we can track via installations through different package managers. So this is a PyPI and Conda. And like you can see, there's basically a huge growth in the last 3 or 4 years. I think this is really great because it's sort of shown that this sort of investment we made in getting students and maintaining the software, even on the verge of death, we sort of made an effort to bring it back to life, and it really worked. And so we had, like, I think last year, 1.7 million downloads. But again, I'm not saying that this is 1.7 million users. It's very hard to understand where all these downloads are coming from. But at least it tells you something that there's a growth in use. And also, it's a nice feature that people use Qtip itself as a sort of dependency in their own software. So there's a huge number of packages which basically rely on Qtip as a backend to simulate quantum systems. Finally, if you want to install Qtip, There's basically 3 or 4 different ways to use it. You can use this Google Colab, which in the example notebook, you can find out how to do it. We have this very funny system called try Qtip, where if you go to this website, it will essentially run Python and Qtip in your browser. This is some sort of magic where you don't even have to install Python. It will just run it in your internet browser locally. So if you're really, really lazy and don't want to install Python at all, this is a fun way to just give it a try. If you want to actually do some development, it's better to have a local version of Python and then use Anaconda or just a normal Python environment. I would say it's better to use Anaconda typically because it tends to be the libraries that Anaconda provides tend to be quite optimized for hardware. So if you can use Anaconda, it's better to do that. And we get a lot of issues of people installing things in Windows. So if you're using Windows, I highly recommend to use this WSL, which is a sort of Linux simulation kernel in Windows. So you can basically run Ubuntu in Windows in a little, command window, and it will solve all your problems. So you'll never have another problem with a Python package ever again. So it's very recommended. Okay, so get on to the actual physics of the Qtip package. So I have this picture which sort of summarizes what's in Qtip in 3 different ways. One is the QObject class, which is essentially what we use to describe vectors, operators, and super operators. Let me put this on here. Sorry. And I'll explain this in a minute, but one new feature that we've provided in this version 5 is that we have a very flexible, what we call a data layer, which means what the actual matrix that represents your Hamiltonian or your state can be represented in different data formats depending on the circumstances. And this particularly is powerful because it lets us use external packages to represent the data, like Google's JAX package, which allows us to do GPU support and auto differentiation, which I'll try and explain a bit later. Once you have a quantum object, you need to do something with it. So the main thing about Qtip is it's a noise simulator. So we saw in Marco's talk, he started to introduce this master equation with some rates that describe decay and so on. So we describe this with what we call this ME-solve, which is a master equation solver for a very general definition of a Lambert master equation. And I would say that probably 90% of what people use Qtip for is for this, I guess. But on top of that, we have a bunch of other stuff, in particular the Heon solver, which I want to talk about tomorrow, and the Blott-Redfield solver, which in some sense is a sort of specific example of a Lambert master equation, but kind of customized and optimized for a specific situation. And then there's plenty of other stuff. I've underlined the orange things that I'm going to talk about. But if any of these are of interest to you, I would say go and have a look in the documentation, basically. We have a new optimal control package. So if you're interested in quantum control, like how to optimize pulses and so on, please give this a try because it's full of bugs at the moment. We only put it in a few months ago, and it's we're trying to iron everything out. I was going to put some slides on this, but I think I ran out of time to make them, and also it's not really my field. And I would say this is an interesting problem in Qtip because we have some features which people have contributed and then left, and no one knows what they do. So for example, like this Floquet master equation, that sounds simple, Floquet master equation, it's Floquet time dependence, and you apply it to master equation. No one could understand what this solver was doing. I think 3 weeks ago, after years, we finally understood the regime of validity of this solver, but the person who wrote it left. The references they provided didn't make much sense. So if you're an expert in any of these things and want to get involved, feel free to, if you find some problem or something doesn't make sense, feel free to leave some feedback. Yeah, okay. Documentation is good. Please document things. Yeah.
What's the Monte Carlo master equation?
So the Monte Carlo master equation, we have like 2 versions. One is MC-solve, which is like you take a master equation and you unravel it in a trajectory sense, so a stochastic trajectory. So you have a sort of non-Hermitian Hamiltonian, and that evolves, and every now and again you might randomly get a quantum jump. And then to get back to the normal master equation, you have to average over all those trajectories. So this is basically a simulation of quantum jumps in some sense. We recently added this non-Markovian NC solve. So what this means is if you have a master equation with some rate that's like time dependent, and perhaps sometimes that rate is like negative, this is a sort of feature of some non-Markovian examples. And I think this example Marco had, where he basically had a rate which was time dependent. And I think we heard this question about, can this describe this coherent Rabi oscillation? A coherent Rabi oscillation is a very non-Markovian thing. And so I expect that if you looked at that rate, it would perhaps have some negative values at certain times to encode this. And what it turns out is that unraveling that sort of master equation in trajectories is very difficult. So we have the solvers to do it, because it is in principle possible, but it converges very, very badly. So it's more of an academic curiosity than a practical numerical tool. But if that sounds interesting, we do have this non-Markovian MC solve. Yeah. So the main thing in QTIP is that we have these quantum objects, which are basically matrices. So a Pauli sigma Z operator is just a 2x2 matrix. And if you want to write it as a quantum object, you can define it in this way and just wrap it in this quantum object initialization function, and it will make it into a QTIP quantum object, which has both the matrix and a bunch of sort of data about properties of that matrix. So it has a shape, which is just a 2x2, has these dimensions, which I'll mention in a moment. And here it assumes it's an operator because it's a matrix and not a vector, and tells you whether it's Hermitian or not, and so on. And so the key thing here is that you could do a lot of QTIP functionality just with matrices, but having this access to this metadata helps you do things. So in particular, these dimensions are a key thing. So for example, we'll see in a later slide that when you have two quantum systems, you take the tensor product of their operators, and then if you just represent that as a big matrix, if you want to, for example, take the partial trace that we also saw this morning, if you don't keep track of the fact that that matrix is made out of a tensor product of two subsystems, you don't know how to take that partial trace just numerically. So we have these dimensions that tell us essentially how the object is constructed. So this, on the other hand, the problem, I don't like these dimensions very much because they're not very human readable. So for example, this is just a list of two numbers. So I have this sort of way to interpret them. In particular, for example, operators here, I like to think that you can think of them as matrices which map vectors to vectors. So this like Pauli matrix maps a two-dimensional vector to a two-dimensional vector. States, on the other hand, map vectors to scalars, so bras and kets. If you take an inner product of a bra and ket, you get a scalar. And super operators, which are also just matrices, but they're act-on operators. So they sort of take operators to operators. So we'll see that a bit later. There's some other important data, which is like the format that the matrix is actually stored in. So here it's just done some default choice of putting it in a dense. This is basically like a NumPy array, essentially a custom NumPy array, dense data format, which stores all four elements of the matrix, in contrast to a sparse format, for example. And you can always get back that sort of array just by calling this function. Once you sort of have these quantum objects, you can just do all the standard arithmetic. That arithmetic is just the arithmetic of matrices. So for example, if you want to build a Hamiltonian, which is the sum of two Pauli operators, we have these built-in functions that give you the Pauli operators, and you can just add them together and get a Hamiltonian, which again is just a matrix with certain properties. These pre-built Pauli operators, you'll notice, have a different data type there. These compressed sparse row, sparse matrices. In this case, the actual data doesn't store any zeros. Here, they're all non-zeros, so it stores everything. But if you have a big sparse matrix, it's a more efficient way to represent it. Then you can also do things like take powers of matrices and so on. This is all very standard matrix algebra. And there's also a bunch of built-ins inside quantum objects. So for example, if you want to take the Hermitian conjugate, you'll take the dagger of this operator. This will sort of flip the off-diagonal elements and take the complex conjugate, we have a built-in trace function, which will take the trace of the operator, and you can at any time calculate the eigenenergies and eigenstates just by calling the function on that object. So every quantum object has access to all these functions. So this is why this is sort of the utility of these quantum objects, rather than just having a bare matrix and just multiplying it around. At least with the quantum object, you have access to all these properties and functions and can do things with them. Also wanted to show basically what a state would look like. So one of the most common functions you'll probably use, you'll define a Hamiltonian, for example, with some operators, normally Pauli operators or some sort of product of creation and annihilation operators. And then to make states, I most normally use this basis function. So what this does is it creates a state which has the number of internal states of large n here. So this is like a 4-level system essentially, and it puts a value of 1 at this index here. So this is a 4-level system with an amplitude of 1 at this index. So if you want a different amplitude, you just multiply it in front of this function. So you do like, if you wanted this to be some sort of superposition of 2 basis functions, you just do 1 over square root 2, 1 plus the other, and so on. And here you'll see this has the type ket. So this is a ket state. And if you take the dagger of this, you get the bra conjugate. Is there anything else to say about these? One minor thing is that it's both nice and annoying that Python, objects count from 0. So for example, we put this number here as 2, but it's in the 3rd position because it counts 0, 1, 2. This is nice because it's the same as what you might do with a Fock state, right? A 0 is a ground state, 1 is the first excited state, 2 is the second excited state. So in that sense, it's nice. But sometimes if you think that you're putting this in the wrong place, you have to remember it essentially. But, everything counts from 0. There's a lot of built-in functions for dealing with these states. For example, you can instead of creating just a discrete state in this vector, you can create things like coherent states. You still have to truncate the space. So a coherent state is essentially a sort of minimum uncertainty state for harmonic oscillators, which are normally infinite dimensional. But here we have to truncate that space. So we do a relatively large number here, and we give an amplitude for this coherent state. And then we can easily plot this in different ways. We can plot the occupation of different Fock states in this coherent state. You can plot the Wigner function. It's very hard to see here, but it's an uninteresting Gaussian blob. But of course, you can do more interesting things like take superpositions. There's another function called Fock, which is essentially the same as basis. And then you can take superpositions of states, normalize them, and also plot their Wigner functions in just a few lines of code. So the point is there's just anything you might want, most things you might want to do, you can just do quickly. So this is why it's better than just having a matrix, essentially. The other thing is, I wanted to maybe say this now, which is that QTIP can also end up being a bit of a black box. For example, particularly when you get to using solvers, advanced solvers like the HEOM and so on. And there's a question of should you trust it? Like if you're putting results in a paper, but you're not really knowing what the solver is doing, or if you've done it correctly, or maybe there's a book somewhere. And I would say basically, no, you should never ever trust anything. And you should always make sure that what you see makes sense from your experience, and also try checking things with multiple different ways, analytical limits, doing different solvers, and so on. So I want to discourage the idea of using these open source things just as a black box, which can lead to sort of disaster in some situations. We have a disclaimer: if there's a bug, it's not our fault. Your result is wrong. So just a minor point I want to mention. So continuing on with some more useful functions, when we start to think about harmonic oscillators, or you might want to define something like an annihilation function of a Fock state, which has these properties. It takes an n photon state to an n-1 state with this prefactor. So here we have this destroy function. Annihilation is too difficult to spell, so I think we chose destroy. And again, you have to truncate this Fock space. This is quite small, so maybe it's hard to see at the back. But you end up with a matrix, which is essentially this annihilation operator in the truncated space. The same for the creation operator. You can quickly construct it. And once you have this object, you can just multiply. This is just A, like you would write on a piece of paper for the annihilation operator of a harmonic oscillator. You can create the photon number operator by doing A dagger A. You can make it interact with the qubit all very, very easily. Yeah. So one other thing. Yeah.
Does it order? It orders from top left.
Yeah. Yeah. So this is again a sort of slightly unintuitive, maybe, because this is the opposite of what the sigma z operator does, for example. So in the sigma z operator, you have 1 minus 1. So in some sense, -1 is your like ground state. For this creation operator, you'll see that this essentially this square root 1 is here. So this first element is sort of your equivalent to your ground state. It's your first excited state, second excited state, and so on. So this again comes from the sort of default ordering in data objects in Python. And I would just say that, for example, if you create the destruction operator, for example, and apply it to a two-level system that you've built out of Pauli operators, it will do the opposite of what you think it should do. So you have to be aware that the ordering here is different from what you might think it is.
Sorry, so what is the Pauli operator? It looks like it's a -1 in the top left. Or what?
So the Pauli operator is normal. So this is why it's a bit confusing. So here you can see actually let me show.
Yeah.
It's just normal. So it's the opposite ordering of these annihilation creation operators. So the difficulty, there's a quite common thing that someone will try and mix these destruction operators for a two-level system and a Pauli operator, but it will do the opposite of what you think you're doing.
Doing the box sphere, and which one?
Yes, that's normal. So the block sphere is what you expect it to be. For most spin things, it's if you use the Pauli operators, it's what you expect it to be. But for these annihilation and creation operators, it's just ordered differently. I don't think I have an example of a block sphere. Yeah. The other thing about these truncated Fock spaces is there's always inevitably to be an error, and it's interesting to see this error in terms of the commutation relations. So when you define these annihilation operators, they're just truncated, right? But they look like what you would expect them to be. But if you calculate the commutator of the two, this should give you this identity operator. And what you find is that it's an identity up to the last element, where suddenly it's -4. And actually, as you increase the Fock space, of course, it's the last element, which is always wrong, and it gets bigger and bigger. There's no real way to remove this error, because you're truncating an infinite dimensional system to a finite space. And the usual idea is that as long as your truncation is large enough relative to where your dynamics or your states are, this shouldn't matter. But it's important to recognize that there is the potential for a truncation error in your simulation if you don't make these matrices big enough. Yeah. So I mentioned a few slides ago that we have this DIMS object to keep track of tensors of composite systems. So we have this function tensor, which just takes the tensor product of two operators or states. So here we're taking a tensor product of a two-level system in its ground state with a two-level system in its ground state. So this is two-level systems as the state of two two-level systems. So this is a 1/4 vector where the dimensions here are like 2, 2, 1, 1. So the fact that this is a tensor of two systems is encoded in the fact that there are multiple numbers here. So this is two-level systems, and each one of them can be thought as of a map to a scalar. There's some argument whether these 1-1s should be written as a continuous list or just a 1. I think we're going to change it because it's a bit confusing. But the key thing is that if you had a 4-level system with a single excitation in it, the dimensions would be 1 times 4. So for most purposes, this is not very important. But if you take this object and multiply it by a vector that's, or take an inner product, for example, with a vector that's a 1/4 dimension, it will fail. So the DIMS will always be checked to make sure that you're combining objects with the same tensor structure, which is an important thing to remember. So having this tensor structure allows us to do this partial trace. The way this works is functionally, for example, here we have basically a highly entangled state, or some sort of bell pair where it's like 0, 1 plus 1, 0, and then we normalize it. So this state psi is a bit similar to the state that Ahsan used for the Bell inequality violation. And if you want to trace out one of these two systems to get the reduced density operator of the other one, you just call this function ptrace and indicate which of the two systems you want to trace, which you want to leave after the trace. Sorry. So you can think of this tensor. You have this order, right? So this is system 0. This is system 1. So we take the partial trace, and we're just left with this system 0. And so this initial vector becomes a 2x2 density operator with just 50-50 population. So it's a totally mixed state. The same we can do with tensor product of operators. So for example, we want to build up a Hamiltonian with two interacting spins. You have to define operators of each spin individually, where you take the tensor of the Pauli matrix with an identity. So this is the operator sigma z acting on one of the two spins and not influencing the other one. So this, as a matrix, this is just looks like this. But it's like a Pauli matrix extended to this bigger space. And then you can do this again and again with arbitrary dimension systems. You can have tensors of two-level systems and n-level systems and so on, whatever you happen to need to do. And then when you need to make coupling terms, you need to define operators, which you can either define these guys independently and just multiply them, or you can explicitly take a tensor of two individual Pauli operators and get, for example, sigma x tensor sigma x, and then you just build the 4x4 matrix that you need. So with this, you can start to do actual physics. So here's a first little example. We want to write a Hamiltonian of two spins that are just interacting with this sigma x interaction. So they have their own energy level splittings, epsilon1 and epsilon2, and some interaction strength G. You define the parameters, you define these operators, and you write the Hamiltonian, and you get this matrix like this. One thing we're thinking about is that whenever you instantiate any operator or Hamiltonian or anything like this, the matrix, we have this flexibility in the data layer of the matrix type, as I'll show a bit later, but the matrix is always created. So this is, in some sense, a bit something we want to change. We want to move to a more symbolic representation and delay creating any matrix. So it would be nice if we could have a Hamiltonian, for example, where we can define it in this structure without defining necessarily the parameters explicitly a priori. And also we can then store how the matrix should be made. And this is very, very useful for things like supercomputing and so on. So we have a little goal here for a future project, maybe a Google Summer of Code, but I think it's quite difficult. Just something I wanted to mention, but the key thing is, as soon as you define the parameters and you find some operator, this exists in memory as a matrix. So now we can do something like solve the Schrodinger equation. So we've seen this many, many times already. So we know this, so the wave function evolves according to the sort of time-dependent Schrodinger equation. So you have a few ways to solve this equation. We saw already that we can just create this propagator, essentially, this unitary operator, which is this exponentiation of the Hamiltonian. However, numerically speaking, this is not necessarily the best choice. We can do this in Qtip. We have this little function, matrix exponential. So you just literally define the Hamiltonian, the time you want to evaluate it for, multiply it by minus. This is the complex number in Python. You take exponential and you'll get the propagator, and then you can just multiply your state and you'll get this solution. But in practice, if your Hilbert space is very large, this is not the best way to do it because, first of all, this operator is very dense. So it has a lot of elements, so it takes a lot of memory to represent it. Secondly, doing this exponentiation There's sort of you can do it there's some options where you can do it in a sort of perturbative way, but if you want it directly, it's basically equivalent to diagonalizing this whole Hamiltonian, which can be numerically challenging if this is a big problem. So instead, we want to think about this problem as just the standard initial value ODE, and then treat it with normal finite difference methods. And we have a huge range of solved methods for this. I think if you will have studied Brunsch, have I spelled this wrong? Brunschkutter, but there's all a bunch of other ones like Adams, there's Verne and so on, which allow you to solve this ODE with different degrees of precision. So to show how to do this, we take this Hamiltonian as we had it defined in the previous slide. We have to define an initial condition. So here we just put a tensor product of one of the spins in its So remember, this is the opposite of what you think it'll be. This is the spin actually excited, and this is the spin in its ground state. And then we define a list of times which we want to solve this Schrödinger equation for. This list of times doesn't actually affect the ODE solver accuracy or anything. It just tells us how far we want to go, 0 to 10 times in some sort of unitless parameters. And we want to return the results of 100 steps between 0 and 10. But that won't affect the accuracy of the solver because it's a dynamic solver which will choose the internal step length itself. And then you just literally call this Schrödinger equation solve, SE solve, with the Hamiltonian, the state, and the times, and you'll get a result object. So this result object, basically, the key thing is it stores the either observables you want to calculate or the states at all those times. So in particular here, it's just stored all 100 states, and you can access those states. It's just a Python list, and then you can calculate expectation values with them and so on. There's a bunch of other data in here, but most of the time, this is not very important. It just keeps track of the options you gave the solver. So if we do this with this Hamiltonian, we have this initial sort of excited two-level system interacting with the other one, and you just see this beating where they're just exchanging this interaction as a function of time. Here I'm just emphasizing again that there's this annoying convention that this basis function is actually excited state, so of the Pauli spin operators. So it's something to be aware of. And then they're just coherently oscillating backwards and forwards forever and ever and ever. So it's pretty standard. So now we want to do something a bit more interesting. We want to introduce noise. So the default way to do this is with a very generic definition of what we call this Lambert master equation. And this Lambert master equation, instead of describing the evolution of a wave function, describes the evolution of the density operator. And we already heard about this, so I don't want to harp on about it. But in the end, you can sort of think of it as a way to combine classical statistics with quantum statistics or wave functions. So we can represent essentially ensembles of wave functions with some sort of classical uncertainty. This functionality in QTIP is very generic in the sense that to set up this problem, you define a Hamiltonian, and then you define these operators. We call these collapse operators, which act on the space of your problem, and then you plug in some dissipation rates, for example, and hope that this gives you the right solution for the problem you're studying. So this is very, very generic. So it's another case where you should sort of keep in mind that you should probably understand a little bit more about your problem before just using a sort of phenomenologically a given master equation. So here what we're doing is we're just doing a bit phenomenologically. We're putting in a Hamiltonian, we're putting in these collapse operators, which just essentially remove energy from each qubit locally. So these are, again, here we take the dagger because the excited state is the ground state in a Pauli operator. And we define this list of operators, which essentially take another annoying convention, which I really hate, but it's too late to change it now. We have to take the square root of this rate and multiply this collapse operator, because this is put in together into this function, and then this gets squared with its complex conjugate, and gamma falls out the front. It's very annoying, but it's too late. We can't change it because it will break everyone's code. So essentially, we have two interacting two-level systems, and each one is sort of locally dissipating energy without taking into effect that they're interacting. But we'll come back to that probably tomorrow. So how do you actually solve this? So there's something technical I want to point out here, which is that this equation is a sort of matrix equation. Here you have a matrix, right? And this is, so if you want to think of this, solving this with finite difference methods, in principle you can just say, I want to, I do sort of small delta t, I define my rho of t plus delta t, it's a function of rho of t, and then I can just do all these matrix multiplications. But the sort of inherited wisdom is that this is not the best way to do it, because all the algorithms people have been writing for 50 years for ODE solving much prefer to have a matrix vector right-hand side, whereas this is sort of a matrix right-hand side. So the standard trick here is to vectorize your density operator. And this maybe is like, in some sense, one of the key things that QTIP does internally, very blindly in the sense that the user will never notice if they're just using the solver. But essentially what it does is it takes something like for example, this is a sort of weird way to write a density operator. And it flips one of the vectors so that instead of having a sort of alpha product of two wave functions, we have a tensor product of two wave functions. So this is essentially equivalent to taking this 2x2 matrix and writing it column-wise as a vector. So we just order it 1, 0, 0, 0, and we get this vector here. So this is also quite a deep thing, and there's a lot of different ways to do this, which lead to a lot of different super operator representations. But essentially the key thing is instead of an operator for the density operator, we now have a vector, which you can think of as a sort of weird artificial tensor product of the system with itself. And this gives us a nice formalism as well to calculate the action of operators on the operator. So for example, in this Lambert master equation, you have things which multiply the operator from the left and from the right, and sometimes both. And with this sort of what is called this Liouville space representation, we can easily calculate the action or the matrix that should be multiplying our vector from the left on its own. So the logic here is that when we take this sort of shift of taking this guy to the left as a vector, we also take the operator b, put it to the left, and take the complex conjugate. So it's acting on this enhanced tensor space in the same way as it would do if it was multiplying from the right. So the key thing is here that we've turned our density operator into a vector, but we've also turned our operators into super operators. And our operators, which were initially, for example, 2x2 Pauli operators or these sort of little collapse operators, are now 4x4 super operators, which seems very counterproductive. We made the problem bigger. Particularly when you want to think about having a very large system where your Hilbert space is large, and you end up basically squaring the size of the matrix that you're representing this master equation in. But still, this in many cases is the best way to do it. We've recently been coming back to this, and we're adding a solver to actually do a matrix product because a lot of GPUs, ODE solvers actually like that more than CPUs do. So that will be a feature we're adding soon. But for most, unless you're attempting to do something sophisticated in creating a very in the background, then you won't notice. So for example, we now have this new setup where we have these two interacting spins. We have this initial condition, these time steps, these collapse operators, and here we define some observables to also return. So we don't need to do it manually. We can just say, I want to get the expectation value of sigma z1 and sigma z2. And instead of this coherently also exchange of energy, we see this exponential decay of amplitudes because both two-level systems are emitting into some environment and losing energy. But as I mentioned, this is sort of just a phenomenological use of a Lambert master equation. And if you really want to do it properly, you need to derive the master equation that you need for your particular problem at hand, a little akin to what Marco was doing. We have a more sophisticated set of solvers to cover a lot of situations, and we'll go through it tomorrow, essentially. But often you might need to do it yourself. So again, it's not like a black box where you can get everything for free. You have to put in the right input to get the right output.
Where do you define the initial density matrix?
So I just defined here that was a while. I use the same initial condition here. So I defined it as a wave function and not a density matrix. But if you give that, it will internally calculate the equivalent density matrix. So you can either give it this can be a ket or it can be a density operator. Yeah. So actually, just to repeat that point. So for example, this situation where we've got these two interacting two-level systems, if this interaction strength is weak, it turns out actually this what you might think of this little phenomenological model I set up is actually not too bad. It's actually quite correct. But if you increase the interaction strength between these two guys, the master equation that in principle gives you the correct dynamics is not one written with the local collapse operators, but what's known as Brest operators. So your Lambert master equation will be defined in terms of eigenstates of your system instead of local operators acting on spins. And we have this block Redfield solver, which will calculate all this for you. And as input, we give spectral densities and temperature, and it will construct this more sort of nuanced master equation. I'm just showing this on one slide today, but I'm going to come back to it tomorrow because I think it's so important. And the key features here are that this master equation is still a Lambert master equation. It still has these collapse operators on the left and right here acting on your density operator. It's still of the same form as before, but these collapse operators are now written as eigenstates of whatever your system Hamiltonian is. And then the emission and absorption into the environment is given by the environment spectral density and the temperature. So if this is a bit new, that's okay, because I think also other people will probably talk about similar things, but also tomorrow I will go over this again and sort of justify where this comes from. But this is quite cool because it's sort of, for example, in the long time limit, it will give you a Gibbs thermal state distribution. So this will properly thermalize your system with the environment, whereas this sort of local operator stuff won't do that. Okay. So the other thing you might want to do is have a driven system. Camille was talking about this, where he wants to like drive his system with a classical field, like a laser or something. And we can support this with an enhanced object. We call this Q object Evo. And the way this works is we basically define an arbitrary time-dependent function, or operator, sorry, with a sum of time-independent operators and arbitrary time-dependent functions. So for example, if you wanted to have a driven qubit, you would define a function which is like a cosine. So this is just a Python function that returns the cosine of t. And then you could, for example, what am I doing here? Okay, I don't actually give an example of that here. But so here, this essentially, sorry, 3 different ways to define the time dependence. I'll be a bit more precise. So either you can define it in terms of a function. So this is just some continuous function, analytical function, you know what it is. You can define it in terms of a string of functions. Basically, nobody ever uses this anymore. This used to be an efficient way to do it because we had a bunch of underlying C code, which would do it very efficiently, but with a bunch of predefined C code functions. But I think nowadays this is it's just as efficient to just call the pure Python function here. And the other way to do it is to just define an array of values. So this is quite useful if you have experimental data, for example, that you want to put into a simulation, and all you have is some discrete data points. So the ODE solver can't operate with just discrete data points. So what it'll do is you can give this, you can create this time-dependent quantum object based on these discrete data points, and internally it will do essentially a kind of cubic interpolation function between the data points so that the solver can still operate with it. And this works really well. We're actually collaborating with a group in Taiwan who are trying to build sort of what they call cryo CMOS, which is like a way to manipulate a actually they're doing spin qubits in a cryogenic environment, and they don't want to put these external wires in with these driving fields. They want to do it on the chip. So and they have this very complicated way to design how these pulses are generated, and we can put them into QTIP and simulate how well their design works in practice. So just as a little example of this, here we have this driven Rabi model, essentially, or so we have a two-level system. So not a Rabi model, but it's Rabi driving rather. So as we heard this morning, so we have a two-level system with this Pauli spin operator, and we're just driving it with this sigma x operator. And if we define this driving function as a sine function, we can set it up with this Q-object evo with this pure sine function here. And then we define some list of operators and time-dependent functions for the Hamiltonian. So the H0 here is just the time-independent part. The H1 is the time-dependent part with the function involved, and our total Hamiltonian is just these list of time-independent and time-dependent parts. Then the syntax here is a bit more complicated than what you saw before, but essentially to define a time-dependent object that we can give to the solver, we can just make it a list of functions and operators. So once we've set that up, we just, again, give it to this master equation solver. We put this list of time-dependent and time-independent operators into this as the Hamiltonian, find initial condition, time steps. Again, we just give a phenomenological collapse operator. And we can do a couple of things. We can check, we can compare it to the rotating wave approximation. So if this drive is on resonance with this two-level system and this amplitude is weak, we can go to a rotating frame where this time dependence can be removed. And you get instead this sort of effective Hamiltonian where if you put this delta is equal to the driving frequency, the effective energy splitting of the qubit for the spin is 0, and then it just precesses under this amplitude of the driving field. And we can also just set this up as another example and compare the two. And because we choose parameters where the drive is very weak, the dissipation is weak, the drive is on resonance, and everything fits perfectly. And actually here we can go even further. We can compare it to this Bloch-Redfield solver with an effective 0 temperature environment and spectral density, and also this HEOM solver. So we'll come back to this tomorrow. This HEOM solver is an exact method for open system problems, in quotations, exact. And I find it very, very useful because, first of all, you can use it to model systems where all these approximations for master equations break down. But you can also use it for situations where they should hopefully be correct. We heard also from Marco this morning, and I was very much agreeing with him, that it's sometimes very difficult to know when you're in the Markovian regime, when your master equation is really valid. And so having another sort of more sophisticated way to check what you're doing is very useful. So hopefully I'll demonstrate that tomorrow. Okay, so I think we're doing okay for time. So this is basically what I've shown is the sort of snapshot of the standard functionality of QTIP. You define operators, you define states, you put it in a solver, you get some result. So what was all this stuff we did for the last 4 years? So essentially what we did is this new data layer. And again, this was largely the work of Jake Lishman and Eric from Sherbrooke. And this is really, really cool. So basically, when you define a quantum object, it either assumes or you can explicitly define it as having a particular data format. And then you can mix and match different objects with different data formats. And internally, it will do automatic conversion. So you can take sparse operators and multiply them with dense vectors. You can then do things like using a GPU with some external package, which I'll show in a moment. There's also been various other improvements and new solver interfaces that make things a bit more efficient because you can set up the problem once and then run it multiple times. And so on and so on, various small things. But this was we started this version 5 really like 4 years ago, and then there's been a huge number of people contributing. There was like 5 GSOC students, all these millions of pull requests and commits and something. So it was really it was a long way to get it finished basically. So as I mentioned, the start of this whole effort for this version 5 was this flexibility in this data layer. And this was something that Eric had been, and I think also Alex had been championing for a while. And so we did this Google Summer of Code thing where we advertised this as a project for a student. And we got this student, Jake, and he basically did it. He basically changed over 20,000 lines of code in QTIP. And the way this works is really amazing. It's sort of, to me, I would talk to Jake and he would explain it. And I'd be like, I have no idea what you're talking about. This is like very, very complicated. And he has this sort of a back-end dispatcher, which will automatically compare data types and convert them as needed. And If you do, you can personally define your own data type. It's fairly when to all the possible, you can always match objects. So just to demonstrate this a little bit for the functionality, I'm not sure this part is particularly interesting, but just to iterate that there's certain default options that are set. States will normally be defined as a dense vector. Things like the Pauli operator will be defined as this sparse CSR, which is a sort of common sparse matrix format where you only store non-zero elements and their location in the matrix in a particular way. We have a custom diagonal sparse format. This was demanded by Alexandra Blaze group in Sherbrooke, because this is particularly convenient for things like annihilation operators, which are just, you have one diagonal in your matrix, as we saw before. So this is a very efficient format for these sort of operators. And then once you've created that, it will just have whatever that data type is. If you want to override it, you can manually set it, or you can use a default option which will set all objects to use a particular format, which I find very useful sometimes. Just a minor thing, if you're a QTIP user, something a little bit changed, which is if you want the underlying data out of the object, you now have to call this data as function. This is a little bit different from version 4. And I think broke many people's code, because a lot of people want to get the data out and do something manually with it, rather than just having quantum objects. So we've got a lot of complaints about that. I'll come back to complaints at the end. We've got a lot of complaints about version 5. But if you also want to sort of in situation change the one data format to another, you have this to function. So if it's for example, initially some diagonal operator, you just say to dense and it will convert it to a dense operator and so on. Not very interesting. But there's a reason for doing some of this. One is that certain operations between data formats are more efficient than other ones. So when you're doing this ODE solver, it's essentially doing a big matrix vector product over and over and over again. And if you look at the different timings of these, then these, like, if you have a sparse times a dense operator, is very fast. But if you have a dense times a sparse, it's very slow. So this is another reason why this sort of matrix multiplication choice might not be the best way to solve an ODE. But on the other hand, this new diagonal format is fast in both directions, which I think is why we added it. This is just a bunch of timing. It's not very interesting. So the more interesting thing is once we have this flexible data layer, we can go out and we can take some existing package and write a custom wrapper for that package. And we had a long-term goal of getting things onto GPUs. People kept telling us GPUs are good for simulations, so if we can support them in some way, we should. So we tried some experiments with Google Summer of Code projects with QPy and TensorFlow, but these in the end were kind of abandoned. We settled on this JAX format. And then this is super popular for people with machine learning, I think. I took some quotes from like Google DeepMinds who say, many people are now moving code into JAX. It's like the DeepMind are using it, I guess, maybe because they're owned by Google and JAX is owned by Google, I don't know. People are moving from PyTorch to JAX and so on. All these companies are moving to JAX. So we thought, oh, let's also do JAX, that sounds good. To get this working, though, there was some problems. So JAX does not have a sparse data format. So Eric went out and coded his own in this diagonal sparse formats. And this is, in some sense, the big effort that we made. So we're taking this JAX off the shelf, using all its functionality, but the default JAX format is dense, which is not particularly useful for if you have a huge master equation that's a very sparse object. So now we have this sparse format. And to use this QTIP JAX, you just have to install it separately from QTIP. You do like pip install QTIP JAX. And then when you define objects, you have to define them as this JAX data format, and then it will just all work as usual. The two big benefits of doing this are we have access to this GPU ODE solver. I'll show this in a minute. And also access to what's called auto differentiation. And I think this is also one of the reasons why this is a very popular package for machine learning. So the way this works is also slightly magic. So my understanding is that, you know, on a computer, it's a very low level, any sort of operations are in the end built out of analytical functions. So if you want to take a differentiate, if you want to differentiate something, if you have access to those very low level analytical functions, you can take derivatives of them. And this is essentially what JAX is doing. So when you make a JAX function, if you build it out of JAX objects, you can take basically derivatives of a function of any parameter. And the cool thing is you can, for example, solve a master equation up to a certain time. Then you can take you can use this JAX auto differentiation. It's just called JAX.grad, and it'll return the derivative of that output at that time as a function of any system parameter. So this is very, very useful for things like optimal control. So you often want to have a control term in your Hamiltonian, and if you change it a little bit, are you going more towards the, you know, the sort of optimal pulse? And typically, one way to do this is looking at gradient descent, where you check if you're going toward, you're sort of going towards some goal function. And to do that efficiently, it's better to have access to derivatives. And so we can basically take a derivative of some, for example, fidelity as a function of a system parameter at any time. And this is sort of quite amazing. You could, of course, do this manually with some sort of complicated loop and do finite difference and stuff. But this essentially does it all for you. Just to give a sort of example here, this is the Ising, one-dimensional Ising model. This is just something a bit more complicated than the 2 spins. It's like n spins now. And they're sort of, all have energy splitting. They're all interacting with their nearest neighbor, sigma x, sigma x. And this is sort of I like to think of this model, this is sort of transverse field Ising model. This is like the E. coli of many-body physics. So if you want to study many-body physics, you'll for some reason always start with this model. So here we have like a little wrapper where we've set up the problem already in another function. We call the solver and we just return this expectation value of sigma z. And so this pure Python function can then be sent to this JAX.grad, and we can take derivatives as a function of, so here we just plot the observables and it's doing some complicated wibbly wobbly stuff, where we can also get access immediately to the derivative of the observable with respect to, for example, the coupling strength between 2 of the spins, or as a function of time, and so on. So it's just a really, really convenient way to get access to some new data that you might not necessarily have easy access to before. On top of that, it also gives you access to GPUs. So if you have a GPU in your gaming PC, or you have some server with GPUs on it, you can basically run ME-solve or SE-solve on the GPU very, very easily. Is there any benefit? So I got access to this, I think this is some NVIDIA A100, which has like 88 gigabytes of RAM, which is one of the more expensive GPUs. And this is sort of a little toy benchmark where I just tried to find out if I basically take this one-dimensional Ising model, I add some noise just to make it into a master equation. The physics of this is not very important. And I just run either ME-solve with the noise or SE-solve, the Schrodinger equation without the noise. And I change the number of spins in the spin chain. And I just set some arbitrary time to evolve the equations up to, and I check how long it takes the solver to give me a result. So how long does solving this equation of motion take on this GPU? And here I sort of benchmark running with JAX on the GPU, running with JAX on the CPU, which is also an option, or just doing the normal Q-tip solver, which uses some default SciPy ODE solver on the CPU. And what you can see is that like there's a kind of crossover where the GPU, which is this blue line, is about 100 times faster than the normal CPU solver. So there's a sort of 100 times benefit to solving this equation of motion. And the same is true for the master equation. The only difference is the number of spins you can fit on 88 gigabytes. Because of this n squared scaling of the Liouvillean superoperator is like half. So at this point, you just run out of memory on your GPU. But still, you can do something. There was another package called Dynamics, which is made by Alice and Bob, which is a sort of company in Paris, and they wanted to also basically have a JAX ODE solver, and it basically does the same thing as this. It's a kind of clone of Qtip with JAX support. Actually, I have maybe I'll just show this because it's kind of funny. They were posting on that their solver is 60 times faster than Qtip. So, but they somehow didn't notice that we also had a JAX GPU solver, which is basically, so I guess they're basically the same. But it's a very nice package. I'm not throwing shade at Dynamics. So we have like 10 minutes left. So I just wanted to advertise a little bit more about these sub packages in Qtip. So we have this Qtip QIP, Qtip QOC, and an older Qtip Qtrol, which is sort of slowly being phased out. This Qtip QIP package is like basically trying to emulate a little bit what Qiskit does, in the sense that you can define a circuit which represents some sort of quantum algorithm. You can simulate it just by running the circuit and put some matrix multiplications, or you can have a sort of what we call a hardware backend or processor, which is a Qtip simulation of a noisy quantum system. And we have sort of various little examples set up, like a spin chain or a superconducting qubit model. And these have some sort of default internal definitions of how to control qubits themselves, what the qubits are. For example, the superconducting qubit example, since we're thinking about transmons, these are actually 3-level systems. So we try to include some error from having an unwanted 3rd level. And then also the shapes of the control pulses and the noise in the pulses and the noise in the qubits are all defined. So you can define a circuit and ask the question, how does it run on this hardware? Does it give me a correct result? And this is the kind of general philosophy of this this package, and this is why it's called pulse level noisy quantum circuits with Qtip. It's not like the most popular circuit simulator out there, but I think it's quite fun to play with. Probably if you're really serious about running, making circuits to run on hardware, some of the commercial packages are better because they do circuit optimization, transpilation and stuff much better than we do. But as a learning tool, and I think this is quite fun. I just wanted to give a little example. So what I tried to do here was, I don't really know any good algorithms. So I thought, oh, maybe I'll just simulate on the circuit the simulation we just did in MESOLVE. So this is a sort of a simulation of a simulation. So we can imagine that we want to simulate the dynamics of 2 spins in a circuit. And the way to do this is like, there's this trotterization approximation. So we imagine that this propagator for our sort of closed system without noise is defined like this, and we can kind of approximate it with this trotter formula by taking these very small dt's here and repeating it many times. And this is a sort of common first way to do a sort of quantum simulation of quantum systems of the dynamics of quantum systems. So we have these 2 Hamiltonians which don't commute, so this is why we have to do this approximation. We can define a bunch of gates that represent 1 time step in this trotterization algorithm. So the first ones are the 2 sort of sigma z's evolution for a small time, and these are sufficient to be defined by the rotation around these z-axis gates, and you define the angle that they get rotated as just epsilon times dt for the time step. And for the interaction, we have to break it down into a sort of slightly more complicated set, which is this Hadamard gate on one of the qubits. So the targets here means which qubit you're applying the gate to. There's a lot of details here I'm skipping over, but I just wanted to give the flavor of how this works. So this is basically defining the 1 step of the quantum circuit. We have to then do this RZX gate, which encodes the coupling between the 2 qubits, and then do another Hadamard, because we don't have a sort of, the hardware we want to run this simulation on of a superconducting processor doesn't have this native sigma x, so we have to break it into parts. And as a circuit for 1 time step, it looks like this. So we apply these rotations around Z. We do this Hadamard, this RZX Hadamard, and this encodes this like small one of these applications of these operators as a sort of simulation. I wanted to also mention this plotting here. This was, for a long time, we relied on an external package for circuit plotting. And last year we had a Google Summer of Code student who made a new custom map. This is fully a matplotlib. So it's very, you don't need to have any external packages. And I also like the fact that the gates are all a little bit chubby. It's kind of cute. So once you've defined this circuit, you can then define a processor. So here we use this superconducting qubit processor, which has all these internal definitions. We load this circuit into the processor. We define an initial condition. Here, these are 3-level systems because they're transmons. We can look at the pulses that this circuit gets compiled into. So it basically takes it and puts it in a bunch of native operations that we define at the Hamiltonian level. This is all a bit complicated, but this is essentially how the hardware that we're simulating is defined. Importantly, we also have like some funny drift term which represents this like unwanted nonlinearity. So just showing the result, we can just take this circuit, run it. So the ideal circuit does what we want it to do. This coherent oscillations we saw with this Schrodinger equation before. The trotterized circuit has a finite error because we take a large time step. We wanted to make sure that we were showing something interesting in this plot. Normally you would take a smaller time step and get a much better result. And then the noisy hardware, which is not very noisy here, does pretty well. I think we put in some very small effective dissipation for the qubits, and we get a simulation of the simulation of the simulation. So it's like a funny example. Anyways, so what are the pros of this package? This is like designed for this noisy, to take advantage of what's in QTIP. So it takes advantage of the fact that we can define arbitrary time dependence. We have all these generic noisy solvers and so on. The cons are that we don't have all this sophisticated circuit optimization or these compilation steps. So often some of them are missing. So if you define a new hardware processor, you have to do a bit of work to translate gates into pulses that can be applied to the hardware. So I think we've been discussing a little bit about the future of this package because it's sort of in a funny place. We in the workshop we had this speaker from INQ, Spencer Churchill, who's some software engineer from INQ, and he was pushing us quite hard to move QIP so that it can also not just have these software backends, but have hardware backends. And he actually set up an example where it would basically do that on INQ. So you could define your circuit, you could define the certain properties of the hardware, and it would upload it to INQ and run it on their hardware. And he was selling us on this idea because a lot of people use Qiskit, for example, but Qiskit is a commercial package in the end. And any day IBM could say, no, you have to pay even to use the software, or they might just change priority and abandon it. So having a sort of academically independent version of this sort of cloud support for hardware seems fun. The downside is just I don't think we can, at least at the moment, it's not possible for us to do it because what you find is, for example, supporting their hardware, we can do it, but then the API changes a few months later and it stops working. And this actually happened. We did have support for Qiskit backend at some point, and it broke, and then no one's fixed it. So we basically just removed it because it's better to just remove something rather than have something that doesn't work. So we've been debating whether to get more students to work on this or ourselves to work on it, but it's just an interesting question. What is the role of this sort of software in this quantum information world? Anyways, just to wrap up today's talk, we have some plans for more future development, like particularly high performance computing. We've been discussing a lot about supercomputer support in a better way. We do support like MPI in terms of distributing, for example, NC solve, these trajectory solvers you can distribute on multiple nodes on a supercomputer, but you can't take an individual any solve or Schrodinger equation or Heon solve and just distribute it across multiple nodes. Because that's quite a sophisticated thing to do. How do you distribute this matrix vector product that the ODE solver needs to do across multiple nodes and share the memory correctly and so on. So we're digging into this a little bit. I think this will inevitably require a sort of semi-analytical representation of your Hamiltonian or master equation because you don't want to build this massive Liouvillean matrix in the first place. Because normally if you want to distribute things across multiple nodes, you're trying to, you don't have enough memory on a single node to represent the problem. So having this analytical representation seems necessary, but And then also there's this problem we've faced where maintenance is difficult. People get new jobs and don't have time. And this happens more often because it's very good because the people who work on open source software demonstrate their capability, and then they often via that route find really good positions. But for us, we're constantly losing our experts. So we rely, for example, on Google Summer of Code to attract new experts. The other thing we need is feedback from users, like what doesn't work and so on. I've had some examples of feedback here, like particularly version 5. Many people complained, oh, this doesn't work and that doesn't work. Well, I think this is very hard to see. This is Garcia Ripley complaining that his package was broken by this update, and we have like 118 open issues on GitHub. It's very hard to constantly reply to all of these. It's like a full-time job, and we don't have the people to do it. But we still want feedback. So if you want to complain, you can go to. Oh, this is really hard to read. You can go to our Google Groups, which is an email list. Which let me. Like if you Google Qtip Google Groups, you'll find this link. And the other thing is to go to GitHub and make an issue. So just make a complaint, and somebody eventually will reply. More recent complaints will get responses. It's like first in, first out, first in, last out. So, anyways, maybe that's enough for today. Thank you for your attention.
Okay, thank you. I just want to know what is it different from Qiskit, this one, and Qiskit and Julia?
Does Qiskit have Julia?
Like Qiskit and Julia,
right?
And this why this one is not? Is it similar with Qiskit?
Qtip, you mean?
Yes.
The closest thing to Qiskit initially is Qtip QIP. So Qiskit is really more of a circuit simulator, whereas Qtip is more of a general open systems solver. Recently, Qiskit do have a separate package, which is more like Qtip. So they have their own more generic open system solver. So there's more overlap now, actually. I forget the name of it. But they're also, there are features that they don't have, for example. So we have this like, back to the beginning. Here we go. So we have this large sort of class of solvers, which I think Qiskit largely just has a standard Lombard master equation solver to emulate noise, but we have a sort of longer history of just adding more solvers. And yeah, but I mean, they also have to say, on the one hand, Qiskit are, they have 200 software engineers or something. I don't know. So it's hard to compete with them. But on the other hand, their priority is more about their hardware.
So this one focus more on other side that Qiskit cannot cover with the packages that they have.
Yeah. So it's more general noise simulations here. Yeah.
Because I can see this like Monte Carlo and others, which you can solve this one by Fortran, maybe this one.
Say again, sorry.
Like with Fortran.
Yeah. Well, I mean, one funny thing is I should mention is that Python is a very inefficient. I think maybe people have studied Python, and Python is very slow. So in the end, any complicated thing that we do in Qtip is not done in Python. So it's either done in Cython, which is like a sort of C version. It's a sort of it's basically Python that gets compiled to C.
The C, which is more of mimicking the C++.
Yeah, it's pure C, but sort of, it's more efficient than pure Python. And of course, like if you use a off-the-shelf ODE solver in Python, at some level, it's running some BLAS library that's written in Fortran in the 70s. So Fortran is still very important. Yeah. Actually, we have a side package, which is a clone of QTIP written in. So if anyone likes Julia, I have a. Where is this? So there is this. This is presented by one of our students. So this is Quantum Toolbox in Julia.
Yeah, okay.
So this is hosted on the GitHub, QTIP GitHub. But it's QTIP means Quantum Toolbox in Python. So the name doesn't quite, Qtij doesn't quite work anyway. So this is written by, he's not got his own photo. It's a guy called Yite from Taiwan and Alberto Mercurio from EPFL. And so Julia is natively much more efficient than Python. Yeah, so if you like Julia, this is a good package to use. There is other alternatives as well, but basically it totally mimics QTIP in the interface. So if you're used to using QTIP and want to use Julia, you can just switch. And
so if you are familiar with Julia, you can try. And also, if you are also familiar with Qiskit, then you are lucky.
Yeah.
Okay. Thank you.
So also
nothing sophisticated, no. So this is really just, so this is not a this is me manually doing it. So I really just define some DT and some total time steps and just do it manually. So I think if you use Qiskit, it has a built-in trotterization function that will probably optimize this. So we don't have this. Yeah, so it's up to, this is just a sort of example really that, yeah. And this is, I think there's also better, how to say, higher order trotterizations, which have less error per time steps, but this is just the easiest one to do.
Yeah, I have one question. I mean, can you come back to the time-dependent master equation?
Ah, sure. Yeah, exactly. I kind of brushed over that because so this kind of example.
Yeah, so maybe the next slide. Yeah, no, it's very small.
Sorry.
Yeah, I think it's this one. Yeah. Yeah. Okay. So now, where is the time? I've got lost.
Yeah,
where is the time dependent in?
So the way I did it here is that let me put the laser pointer on here. There's different ways to do it, but the way we did it here is we define our Hamiltonian now as this list of two Hamiltonians.
Mm-hmm.
One of them is just the time independent part, so this sigma z here. The other one is this and the function. So this function is just
okay, you define it there. Okay.
And then this is this list is now just what you give the solver.
Okay.
So the time dependence is just in. So this can be a longer list of more and more operators with different functions.
Okay. Yeah.
Or one of the other formats like this array of values.
And so yeah, this is for the Hamiltonian. Can you also have a jump operator which are time dependent?
Yep.
Okay.
Yeah, I don't have a good example for that. Actually, I was thinking, it'd be nice to do Marco's example from this morning with.
Functions again with base n0 sort of excited stuff.
We define the Pauli operator. We just want to define it in the normal way people do on a piece of paper.
Yeah.
So then, sort of, if you define a vector for a state on this, of this two-level system, the sort of basis 2,0 will be the excited state, and basis 2,1 will be the ground state, because this is the lower energy state. On the other hand, if you defining a harmonic oscillator in a Fock space.
So for n larger than 2, I mean, then that it change the order, right?
Change the order. So I mean, it's up to you to decide what order you want things.
Okay.
But in this case, if you define this, where there's annihilation and creation operators, for example, and define a Hamiltonian A dagger A, then this first element will be the ground state.
So 0 is the ground state.
Yeah.
Okay, so yeah, that's why I was confused. So when it's n equal to 2, it's
I mean, you could also define it yourself differently, just artificially. If you use the default Pauli matrix, it's a slightly annoying choice, but yeah.
Yeah, no, it's, just have to know it. Okay, all right. Thank you.
I had one. It's maybe a question better for tomorrow in the next lecture. But is it possible to like easily? So you have like the Lindblad solver, the block Redfield solver, and the HUM. Is it easy to kind of mix these solvers? So like, say for example, you have an equation of motion like HUM, and you want to add like a Lindblad dissipator. Is it like possible to easily mix the kind of solvers?
I don't have an example of that tomorrow, but it's the way it would work is when you call this HUM solver, instead of giving a Hamiltonian, you give a super operator that has your master equation defined inside, and that will just be used in the HUM. So you can mix and match. Whether that's correct or not is debatable, but you can do it.
Cool. Thanks. There's no other questions, and we can thank speaker again.